Hello there, and welcome. Tonight I want to take you somewhere special, somewhere quiet and vast, where time moves differently than it does here in your room. Close your eyes for a moment if you'd like, and imagine yourself floating gently above the earth, looking out into the endless darkness sprinkled with stars. It's peaceful here, isn't it? No rush, no urgency. Just the gentle turning of worlds and the soft whisper of cosmic winds that we cannot feel but somehow know are there. Tonight, we're going to follow a trail that stretches across thousands of years, a mystery written in ice and dust and starlight. It's a question that might seem impossible at first, perhaps even a bit fanciful, but stay with me, because what if the ancient astronomers, those patient watchers of the night sky, who had no telescopes, no computers, no modern instruments, what if they saw something coming that we've only just rediscovered? What if a comet that visited us recently, a ghostly visitor named 3I Atlas, was somehow predicted, or at least witnessed, by our ancestors who carved their observations into clay tablets and painted them on temple walls? You see, in the early months of 2020, while the world was turning its attention to earthly concerns, something remarkable was happening in the outer reaches of our solar system. A comet designated 3I Atlas was beginning its long fall toward the sun. Astronomers had discovered it just months before, a faint smudge of light in their telescopes, barely distinguishable from the countless stars surrounding it. But this wasn't just any comet. As scientists studied its path, its composition, its behavior, they began to realize that this visitor might be connected to something much older, something that perhaps had been seen before, long before our modern era. The comet seemed to be following a path that was hauntingly familiar, an orbit that suggested it might be a fragment of a much larger comet that had graced our skies in 1844, and perhaps, just perhaps, even earlier than that. Now, I know what you might be thinking. How could ancient peoples, without our technology, without our understanding of orbital mechanics, possibly predict or even meaningfully observe something that we, with all our advanced instruments, barely noticed until it was already approaching? It's a fair question, and one that deserves our gentle consideration. But consider this. The night sky of our ancestors was far darker than ours, unpolluted by artificial light, and they watched it with a dedication and patience that we can hardly imagine today. Generation after generation, they passed down their observations, their stories, their warnings and wonderings about the lights that moved against the fixed backdrop of stars. They had different names for these wanderers, these temporary visitors to their skies. Some called them bearded stars, others saw them as dragons or serpents stretching across the heavens, and still others interpreted them as messages from the gods, omens of change written in light and ice. The story of 3I Atlas begins, as so many cosmic stories do, with a discovery that almost didn't happen. In December 2019, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic astronomical survey system designed to detect near-Earth asteroids, spotted something unusual. It was faint, so faint that it could easily have been missed, just a tiny blur moving slowly against the background stars. But the computers flagged it, the astronomers took notice, and soon telescopes around the world were turning to track this new visitor. They gave it a name, following the conventions of astronomical nomenclature: Comet C 2019-Y4, though it would become known more commonly as Comet Atlas, or when scientists began to suspect its deeper connections, through Associate Atlas. As we settle into this story, perhaps you're already feeling the gentle pull of sleep, and that's perfectly fine. Let these words wash over you like waves on a distant shore, carrying you along on their rhythm. There's no need to remember every detail, no test at the end, just a journey we're taking together through space and time. The comet we're following doesn't care if we're awake or dreaming. It continues on its path regardless, as it has for millennia, as it will for millennia to come. And perhaps that's part of its beauty, this indifference to our small human concerns, this reminder that we are part of something so much larger than ourselves. In those early days of 2020, as astronomers calculated the comet's orbit, they discovered something intriguing. The path it was following seemed remarkably similar to that of another comet, one that had appeared in 1844 and had been one of the great comets of the 19th century. That earlier comet had been visible to the naked eye, a brilliant visitor that had captured the world's attention. Could these two comets be related? Could they be fragments of an even larger, more ancient comet that had broken apart sometime in the distant past? The mathematics suggested yes, the observation supported it, and suddenly what had seemed like a minor discovery became part of a much larger story. A story that might stretch back not just decades or centuries, but millennia. Think about that for a moment. A comet that our ancestors might have seen, breaking apart in the darkness of space, its fragments continuing on their separate but related paths, returning to the inner solar system at different times, like members of a family coming home for irregular reunions. One piece in 1844, bright enough to inspire awe and perhaps fear. Another piece in 2020, fainter but still carrying the same cosmic DNA, the same composition of ice and dust that had formed in the earliest days of our solar system. And perhaps if we look carefully enough, if we read the ancient texts with new eyes, we might find evidence of earlier visits, earlier fragments of this cosmic family appearing in our skies when humans were just beginning to record their observations of the heavens. The ancient Babylonians, those meticulous observers of the night sky, left us thousands of clay tablets covered in cuneiform script. Among their careful records of planetary positions and lunar phases, they also noted the appearance of unusual celestial phenomena. They called comets wild sheep sometimes, seeing in their fuzzy appearance and unpredictable paths something akin to animals wandering across the celestial pastures. They recorded their appearances with the same careful attention they gave to eclipses and planetary conjunctions, understanding that these were significant events even if they didn't understand the physics behind them. Could one of their wild sheep have been an earlier fragment of the comet family that includes 3I Atlas? The tablets don't give us enough detail to be certain, but the possibility lingers in the air like the scent of rain before a storm. The Chinese astronomers were perhaps even more dedicated in their observations. For over 2,000 years they maintained continuous records of celestial events, creating the longest unbroken astronomical record in human history. They called comets broom stars or guest stars, and they noted not just their appearance but their colour, their brightness, their path across the sky, and how long they remained visible. In their records, we find mentions of comets that appeared at intervals that might, just might, correspond to the orbital period of our cosmic family. A bright comet in 1106, another in 574, and going back even further, mysterious mentions of great lights in the sky that terrified and amazed our ancestors. Were these all random, unrelated visitors, or were some of them earlier appearances of the same broken comet, returning again and again to remind us of the cyclical nature of cosmic events? As you drift deeper into relaxation, perhaps you can imagine yourself as one of those ancient observers standing on a hilltop or a temple roof, watching the sky slowly wheel overhead. There's no hurry here, no schedule to keep. The stars move at their own pace, and you have all night to watch them. Feel the cool night air on your skin, hear the distant sounds of the sleeping world below. And then, perhaps over many nights, you notice something new, a fuzzy star where no star should be, moving slowly against the fixed constellations. You don't know what it is, this visitor, but you know it's important. You make a note, perhaps on clay, perhaps on papyrus, perhaps just in the oral tradition that you'll pass down to your children. You're part of a chain of observers that stretches from the deep past to the far future, each adding their small piece to humanity's understanding of the cosmos. The story of 3I Atlas took an unexpected turn as it approached the sun. Comets are fragile things despite their cosmic grandeur. They're made mostly of ice and dust, materials that formed in the cold outer reaches of the solar system billions of years ago. As they fall toward the sun, the increasing heat causes the ice to sublimate, turning directly from solid to gas, creating the beautiful tail that we associate with comets. But this process also weakens the comet structure, and sometimes, as happened with 3I Atlas, the comet simply falls apart. In March and April of 2020, astronomers watched as the comet began to fragment, breaking into smaller and smaller pieces until it was no longer visible, even to our most powerful telescopes. It was a gentle disintegration, a quiet ending to what had promised to be a spectacular show. But perhaps this too was predicted, or at least observed, by our ancestors. Many ancient texts speak of celestial objects that appeared and then vanished, stars that grew bright and then faded away. The Mayan astronomers, with their incredibly accurate calendar and their deep understanding of celestial cycles, recorded events that might have been cometary fragmentations. They understood that the cosmos was not static but dynamic, full of change and transformation. In their mythology, they spoke of celestial serpents that would appear in the sky, stretch across the heavens, and then dissolve back into the darkness. Were these just myths? Or were they observations clothed in the language of story and symbol? The Egyptian astronomers, working from their temples along the Nile, also left us tantalizing hints. In the pyramid texts, some of the oldest religious writings known to humanity, there are references to celestial phenomena that don't quite match anything we see regularly in our skies. They speak of stars that swim across the heavens, of lights that appear and disappear according to cycles that we don't fully understand. The Egyptians were particularly interested in any celestial event that might relate to the flooding of the Nile, the annual event that their entire civilization depended upon. Did they notice correlations between cometary appearances and earthly events? Did they, in their own way, try to predict when these visitors would return? We must be careful here, treading gently between speculation and evidence. It's tempting to see patterns where none exist, to read into ancient texts meanings that their authors never intended, and yet we also must remain open to the possibility that our ancestors knew more than we give them credit for. They may not have understood the physics of orbital mechanics, but they were keen observers, and they had something we lack: generations of uninterrupted observation, cultures that valued the slow accumulation of celestial knowledge, and skies dark enough to see even faint phenomena that we might miss in our light-polluted modern world. Consider the Aboriginal Australians, whose oral traditions stretch back tens of thousands of years, possibly the longest continuous cultural tradition on Earth. In their stories, they speak of celestial events with remarkable accuracy. They have stories about stars that fell from the sky, about lights that appeared and disappeared, about cosmic events that modern astronomers have been able to correlate with actual supernovae, meteor impacts, and yes, possibly cometary appearances. Their tradition of passing down astronomical knowledge through song and story created a kind of cultural memory that preserved observations across millennia. Could they have observed and recorded earlier appearances of the comet family that includes 3I Atlas? The connection between 3I Atlas and the Great Comet of 1844 gives us a fascinating window into how comets can break apart and return as multiple objects. The Great Comet of 1844, officially designated C1844Y1, was a spectacular sight. It was visible to the naked eye for several weeks, with a tail that stretched across a significant portion of the sky. People around the world observed it, from the observatories of Europe to the temples of Asia to the indigenous communities of the Americas. It was bright enough to be seen during daylight hours at its peak, something that only the greatest comets achieve. Newspapers of the time were filled with accounts of this celestial visitor, mixing scientific observation with religious interpretation and popular superstition. Now imagine that this great comet of 1844 was itself just a fragment of something even larger, something that had broken apart perhaps centuries or millennia earlier. Each fragment would continue on a similar but slightly different orbit, returning to the inner solar system at different times. Some fragments might be large and bright, like the 1844 comet, while others might be smaller and fainter, like 3I Atlas. And there might be other fragments still out there, slowly making their way back toward the sun, carrying with them the same ancient ice that formed when our solar system was young. This idea of cometary families isn't just speculation. We've observed it happening with other comets. The most famous example is probably Comet Shoemaker-Levy 9, which astronomers watched break apart and crash into Jupiter in 1994. Before its dramatic end, the comet had broken into a string of fragments, each following slightly different paths but all headed for the same destination. We've also observed the breakup of Comet Linear in 2000 and Comet Schwarzmann-Wachmann 3, which has been fragmenting for decades. Each of these events shows us that comets are more fragile and dynamic than we might imagine, constantly reshaping themselves and creating new patterns in their eternal dance around the sun. The mathematical analysis of 3I Atlas's orbit revealed something remarkable. Not only did it seem to be related to the 1844 comet, but both of them appeared to be following orbits that would have brought a progenitor comet close to Earth roughly every 600 years. Now, 600 years isn't a precise number here, and orbital periods can vary due to gravitational perturbations from the planets, especially Jupiter, which acts like a cosmic shepherd, nudging comets into new paths. But if we work backward from 1844, subtracting roughly 600 years at a time, we get some intriguing dates, around 1244, around 644, around 44 CE, around 556 BCE, and so on. Do any of these dates correspond to recorded cometary observations in ancient texts? In fact, some of them do. Chinese records mention a great comet in 1264. Not exactly 1244, but close enough given the uncertainties in orbital calculations. There are records of significant comets around 676 CE. Again, not exact, but tantalizingly close. And as we go further back, the correlation becomes harder to establish. Partly because records become scarcer and less precise, and partly because the orbital calculations become less certain the further back we extrapolate. But the possibility remains, could ancient astronomers have seen earlier appearances of this cometary family and recorded them in ways we're only now beginning to understand? The Greeks and Romans also left us accounts of comets, though often mixed with mythology and political interpretation. They saw comets as omens, usually of disaster, but sometimes of great change or the birth of important figures. The comet that appeared after Julius Caesar's assassination was interpreted as his soul ascending to the heavens, and it became a powerful political symbol. Pliny the Elder, in his Natural History, attempted to categorize different types of comets based on their appearance, showing that even in ancient times people recognized that not all comets were the same. Could some of the comets he described have been members of our cosmic family? As we contemplate these connections across time, it's worth pausing to consider what it means for us, here and now, lying comfortably in our beds to be connected to observers who lived thousands of years ago. We're all looking at the same sky after all, just from different points in time. The photons of light that reach their eyes from distant stars are siblings to the photons reaching our eyes tonight. We're all made of the same star stuff, as Carl Sagan so beautifully put it, and we're all participants in the same cosmic story. The comet that they might have seen and the comet we tracked with our telescopes are made of the same primordial ice, formed in the same distant reaches of our solar system, following paths determined by the same laws of physics. But let's return to our specific mystery. Was 3I Atlas actually predicted in ancient texts? The honest answer is that we don't know for certain, and perhaps we never will. The ancient texts are often ambiguous, using language and symbolism that we don't fully understand. When a Babylonian astronomer wrote about a wild sheep appearing in a certain constellation, was he describing a comet, a nova, a conjunction of planets, or something else entirely? When Chinese astronomers recorded a guest star, were they seeing a comet, a supernova, or perhaps a bright meteor? The uncertainty is part of what makes this mystery so compelling. were detectives trying to solve a case where the witnesses spoke different languages, used different conceptual frameworks, and left us only fragmentary evidence. Yet there are some intriguing correlations that deserve our attention. In the ancient Indian astronomical text, the Surya Siddhanta, which may date back to the 4th or 5th century CE, but contains knowledge that might be much older, there are references to celestial cycles that don't correspond to any regular planetary motions. Some scholars have suggested these might be attempts to predict or record cometary returns. The text speaks of certain celestial events recurring after periods that, when converted to modern units, come surprisingly close to the orbital periods we calculate for some long-period comets. Is this coincidence, or were ancient Indian astronomers tracking something we're only now rediscovering? Similarly, in the Mayan Dresden Codex, one of the few Mayan books to survive the Spanish conquest, there are tables that seem to predict celestial events far into the future. Most of these clearly relate to the movements of Venus and other planets, but some entries remain mysterious. Could they be attempts to predict cometary returns? The Mayans were sophisticated enough in their astronomy to track the precise movements of planets over centuries. It's not impossible that they might have noticed patterns in cometary appearances as well. The medieval Islamic astronomers, the inheritors and preservers of both Greek and Persian astronomical traditions, also provide us with tantalizing hints. They were meticulous observers and mathematical innovators, developing new techniques for calculating celestial positions and predicting astronomical events. In their writings, we find references to hairy stars that appeared at certain intervals, though the intervals they record don't always match our modern calculations. Were they tracking different comets? Or were their observations affected by factors we don't fully understand? The atmosphere was different then, perhaps clearer in some ways, and they were observing from different latitudes than most modern observatories. As you continue to relax, letting these thoughts drift through your mind like clouds across a summer sky, consider how remarkable it is that we're even able to ask these questions. The fact that humans have been watching the sky for millennia, recording what they saw, passing down their observations through countless generations, is itself a kind of miracle. Each observation, each record, each story is a thread in a vast tapestry that connects us all. When we look at 3A Atlas through our modern telescopes, we're adding our thread to that tapestry, continuing a tradition that stretches back to the very dawn of human consciousness. The fragmentation of 3A Atlas in 2020 was observed by telescopes around the world, and the data was shared instantly across the internet, analysed by computers and discussed by astronomers who might never meet in person. Compare this to how our ancestors would have observed a similar event, standing on a hillside or a temple roof, watching night after night as the comet gradually faded from view, perhaps discussing what they saw with a small group of fellow observers, recording their observations on clay or papyrus, or in oral traditions that would be passed down through generations. Both approaches have their own beauty, their own validity. We have gained so much in our ability to observe and analyse, but perhaps we've lost something too, the intimate personal connection with the night sky that our ancestors experienced. The question of whether 3I Atlas was predicted in ancient texts leads us to a deeper question. What is the nature of knowledge itself? Our modern scientific knowledge is precise, quantitative, and testable. We can calculate the orbit of a comet to extraordinary precision, predict where it will be years in advance, and understand the physical processes that govern its behaviour. But ancient knowledge was different. It was often qualitative rather than quantitative, embedded in stories and symbols rather than equations, passed down through tradition rather than written in textbooks. Both forms of knowledge are ways of understanding our place in the cosmos, and both have value. Perhaps the ancient observers who might have seen earlier appearances of our cometary family understood something that we sometimes forget in our modern, fast-paced world, that the cosmos operates on timescales far beyond human lifetimes, that patience and long-term observation can reveal patterns invisible to hurried observation, and that there is profound value in simply watching and wondering. They didn't need to understand the physics of cometary orbits to appreciate the beauty and mystery of these celestial visitors. They didn't need to know that comets were made of ice and dust to recognize them as significant events worthy of recording and remembering. As we move deeper into our exploration, the story becomes both more complex and more beautiful. The comet 3I Atlas, which seemed at first to be just another faint smudge in our telescopes, has led us on a journey through time and space, connecting us with observers across millennia, raising questions about knowledge and observation, and reminding us of our place in the vast cosmic dance. Whether or not it was specifically predicted in ancient texts, it has certainly fulfilled one of the roles that comets have always played in human culture. It has made us look up, wonder, and contemplate our connection to the cosmos. The night is still young in our journey, and there is so much more to explore. As you settle deeper into comfort, perhaps adjusting your pillow or pulling your blanket a bit closer, know that we're going to travel even further into this mystery. We're going to explore what modern science tells us about cometary orbits, and how we might use this knowledge to search for patterns in ancient observations. We're going to visit the great observatories of the past, from Stonehenge to Angkor Wat, and consider how these structures might have been used to track celestial visitors. We're going to delve into the rich mythology surrounding comets, exploring how different cultures interpreted these mysterious lights in the sky. But for now, in this moment, let's simply appreciate the mystery itself. Somewhere out there, in the cold darkness beyond Neptune, there might be other fragments of the same ancient comet that gave us both the Great Comet of 1844 and 3I Atlas. They're slowly falling toward the sun, following orbits that will bring them into our skies decades, centuries, or millennia from now. Future generations will observe them, just as we observed 3I Atlas, just as our ancestors might have observed earlier fragments. Each appearance is both an ending and a beginning, a return and a departure, an answer that raises new questions. The cosmic perspective has a way of putting our daily concerns into context. Whatever worries or stresses you brought with you to bed tonight, they're still real, still important in the context of your life. But they're also part of a much larger story, a story in which comets return after centuries, in which the same laws of physics that govern distant galaxies also govern the atoms in your body, in which you are both insignificantly small and cosmically significant. You are made of elements forged in the hearts of stars. You are a way for the universe to know itself. And you are part of an unbroken chain of observers stretching from the deep past to the far future. As we prepare to dive deeper into the science of cometary orbits, to explore how these icy visitors trace their path through the solar system, remember that there's no need to understand everything, no need to stay alert and focused. Let the information wash over you like gentle waves, absorbing what feels interesting, letting the rest simply pass by. The comet doesn't care if we understand it perfectly. It continues on its path regardless. And perhaps there's a lesson in that. Sometimes the journey is more important than the destination. Sometimes the question is more valuable than the answer. And sometimes the mystery is more beautiful than the solution. The story of 3 Atlas is far from over. Even though the comet itself has fragmented and faded from view, its legacy continues. The data collected during its approach and disintegration will be analysed for years to come, revealing new insights into the nature of comets, the history of our solar system, and perhaps, if we're lucky and careful in our analysis, connections to ancient observations that we haven't yet recognised. Every comet we observe adds another piece to the vast puzzle of our cosmic neighbourhood, helping us understand not just where we are, but where we've been and where we're going. And speaking of where we're going, our next chapter will take us even deeper into the cosmic river of time. We'll explore how time itself moves differently at cosmic scales, how a comet's journey of thousands of years is but a brief moment in the life of our solar system, and how this perspective can help us understand both the possible connections between ancient observations and modern discoveries, and our own place in the vast sweep of cosmic history. We'll consider how the same comet that might have been observed by ancient Babylonian astronomers could still be returning to our skies, changed but recognizable, like an old friend who visits rarely but is always welcome. The universe is patient with us, giving us countless opportunities to observe, to learn, to wonder. Each night the stars return, each year the planets trace their familiar paths, and every so often, a comet appears to remind us that not everything in the cosmos is predictable, that there are still surprises waiting for us in the darkness. 3I Atlas was one such surprise. A gentle reminder that even with all our technology and knowledge, we're still just beginning to understand the complex, beautiful, sometimes fragile nature of our cosmic neighborhood. As we transition to exploring the vast scales of cosmic time, remember that you're part of this story too. Right now, as you lie there listening to these words, you're on a planet that's spinning at over 1,000 miles per hour at the equator, orbiting the sun at 67,000 miles per hour, and moving with our entire solar system through the galaxy at nearly 500,000 miles per hour. Yet it all feels perfectly still, perfectly peaceful. That's the magic of our cosmic situation. We're part of an incredibly dynamic, fast-moving system, but we experience it as stability and calm. The same is true for the comets we've been discussing. They're hurtling through space at tremendous speeds, but from our perspective, they appear to drift slowly across the sky, taking weeks or months to trace their paths through our constellations. Time, as Einstein showed us, is not absolute but relative. It flows differently depending on where you are and how fast you're moving. For a comet falling toward the sun from the outer reaches of the solar system, time passes just slightly differently than it does for us here on Earth. It's a tiny difference, measurable only with the most precise instruments, but it's real. And when we expand our perspective to cosmic scales, these differences become more pronounced. A journey that takes a comet 600 years might seem like an eternity to us, but it's just a heartbeat in the life of our solar system, which has been around for about 4.6 billion years. If we compressed the entire history of our solar system into a single year, a 600-year cometary orbit would take about 4 seconds. The entire recorded history of human civilization would flash by in less than a minute. This cosmic perspective doesn't diminish the importance of human observation and recording. If anything, it makes it more remarkable. In our brief time as a species capable of recording and analyzing celestial events, we've managed to piece together an understanding of processes that operate on timescales far beyond individual human lives. We've learned to read the history of the universe in the light of distant stars, in the rocks of our own planet, and yes, in the ice and dust of visiting comets. Each comet is a time capsule, preserving material from the early solar system, carrying it through billions of years to deliver it to our telescopes and, occasionally, to our atmosphere when meteors, which are often cometary debris, burn up in brilliant displays. The ancient observers who might have seen earlier appearances of the comet family that includes 3I Atlas were working with the same fundamental reality we work with today. The cosmos is vast, time is deep, and we are brief. But they found ways to extend their reach across time through careful observation and faithful recording. They built monuments aligned with celestial events, created calendars that could predict eclipses centuries in advance, and told stories that preserved astronomical knowledge across generations. In their own way, they were doing exactly what we're doing, trying to understand our place in the cosmos, trying to find patterns in the celestial dance, trying to connect the brief span of human life to the vast cycles of cosmic time. As we continue our journey through this cosmic mystery, remember that every question we ask, every observation we make, every story we tell about the cosmos becomes part of humanity's collective understanding. Somewhere, perhaps, a future astronomer will read about 3I Atlas and its possible connection to ancient observations, and they'll add their own piece to the puzzle. They might have tools we can't imagine, perspectives we haven't considered, knowledge we haven't yet discovered. But they'll be part of the same tradition, the same long conversation between humanity and the cosmos that began when the first human looked up at the night sky and wondered what those lights might be. The story continues, the mystery deepens, and the night is still young. As we prepare to explore the specific details of 3i Atlas, its discovery, its journey, and its ultimate fragmentation, let yourself sink deeper into relaxation. There's no rush, no deadline, no need to remember everything. Like the comet itself, we're on a journey that will take as long as it takes, following a path that's both predetermined by the laws of physics and full of surprises. The cosmos is speaking to us in its own language, a language of light and motion, of patience and persistence, of cycles and changes. All we need to do is listen, watch, and wonder. The transition between our chapters is like the transition between sleep and waking, or between one season and the next, gradual, natural, almost imperceptible. We've been laying the groundwork, setting the stage, preparing our minds for the deeper exploration to come. The mystery of whether 3i Atlas was predicted in ancient texts is really multiple mysteries woven together. The mystery of cometary orbits, the mystery of ancient observations, the mystery of how knowledge is transmitted across generations, and ultimately, the mystery of our own cosmic significance. Each thread we follow leads to new questions, new connections, new wonders. Imagine time as a vast, slow-moving river, carrying everything from the birth of stars to our own quiet moments. This river doesn't flow at a constant rate. Sometimes it seems to rush, sometimes it seems to barely move at all. For a mayfly whose entire life spans just a day, the river would seem almost frozen. For a mountain slowly eroding over millions of years, the river would seem to race. For us, somewhere in between these extremes, the river flows at just the right pace to allow us to observe patterns, to make connections, to build understanding. We can watch the seasons change, see comets return, track the slow procession of the equinoxes. We exist at just the right scale to be cosmic observers. In this cosmic river of time, comets are like messages in bottles, thrown into the current long ago and occasionally washing up on our shores. Each one carries information about the conditions when it formed, about the journey it's taken, about the forces that have shaped it. When 3i Atlas appeared in our skies, it was carrying information from the early solar system, from its previous passages through the inner solar system, from its possible connection to the Great Comet of 1844, and perhaps to even earlier apparitions. We try to read this message, to decode its meaning, but like many cosmic messages, it was written in a language we're still learning to understand. The timescales involved in cometary motion can be difficult to grasp. When we say a comet has a 600-year orbit, what does that really mean? It means that when the comet last passed through our skies, the world was a completely different place. If the Great Comet of 1844 and 3i Atlas are indeed fragments of a comet that appeared around 1244, that earlier appearance would have been witnessed by people living in the High Middle Ages. The Mongol Empire was at its height. Marco Polo hadn't yet travelled to China, and the Black Death was still a century in the future. If there was an appearance around 644, it would have been during the early expansion of Islam, when the Byzantine Empire still controlled much of the Mediterranean, and when Anglo-Saxon kingdoms ruled England. Each return of the comet marks a completely different chapter in human history, yet the comet itself remains essentially unchanged, following the same laws of physics, tracing nearly the same path through space. This perspective can be both humbling and inspiring. We're temporary residents in a cosmos that operates on scales far beyond our brief lives, yet we've managed to discover these scales, to measure them, to begin to understand them. Every ancient astronomer who recorded a guest star or a bearded star was contributing to this understanding, even if they didn't know it. Every modern observation adds another data point to our growing picture of how the solar system works, how comets behave, how the past connects to the present and the future. The river of cosmic time carries more than just comets, of course. It carries planets in their stately orbits, stars in their longer journeys around the galaxy, galaxies in their even longer dance with each other. It carries the gradual evolution of the universe from its hot, dense beginning to its current vast, cool expanse. And it carries us, brief observers trying to understand our place in this grand flow. We're like people standing on a bridge over a river, able to see a small section of the flow, trying to understand from this limited view where the river comes from and where it's going. As you lie there, perhaps feeling yourself beginning to drift towards sleep, you're experiencing your own personal flow of time. Your heartbeat marks seconds, your breath marks a slightly longer rhythm, your daily cycle of sleep and waking marks a full rotation of our planet. These are your natural timekeepers, the rhythms that govern your life. But you're also part of longer cycles, the annual journey around the sun, the longer cycles of climate and weather, the even longer cycles of geological and evolutionary change. And through your awareness of comets like 3I Atlas, you're connected to cycles that span centuries and millennia. The ancient observers who might have recorded earlier appearances of our cometary family were working with these same nested cycles of time. They noticed that the moon went through its phases every 29.5 days, that the sun returned to the same position relative to the stars every 365 days, that the planets traced complex but predictable paths through the constellations. They built elaborate systems to track these cycles, to predict when they would repeat, to understand the clockwork of the heavens. And occasionally something would appear that didn't fit the pattern, a comet, a nova, a meteor shower, and they would record it, wonder about it, try to fit it into their understanding of how the cosmos worked. We're still doing the same thing today, just with more sophisticated tools and a deeper understanding of the underlying physics. When 3I Atlas appeared, astronomers immediately began calculating its orbit, comparing it to known comets, trying to understand its place in the grand scheme of things. The discovery that it might be related to the Great Comet of 1844 was exciting, because it suggested a pattern, a cycle, a connection across time. And the possibility that both comets might be fragments of something even older, something that might have been observed by ancient astronomers, adds another layer to the mystery. The fragmentation of comets, which we observed happening to 3I Atlas in 2020, is itself a fascinating process that connects different timescales. The fragmentation event itself might happen over just days or weeks, as the stresses of solar heating and tidal forces tear the comet apart. But the consequences of that fragmentation play out over centuries or millennia, as the fragments continue on slightly different orbits, returning at different times, creating a family of related comets where once there was a single object. It's like watching a family tree develop, but instead of generations of people, we're seeing generations of comets, all descended from a common ancestor. This process has probably been happening throughout the history of the solar system. Many of the comets we see today might be fragments of larger comets that broke apart long ago. Some scientists estimate that most short-period comets, those with orbits of less than 200 years, are fragments of larger bodies. This means that when we observe a comet, we're not just seeing a single object but potentially part of a vast extended family, scattered across different orbits, returning at different times, but all carrying the same primordial ice from the early solar system. The ice in comets is particularly interesting from a temporal perspective. It formed in the cold outer reaches of the solar system over 4.6 billion years ago, when the sun was young and planets were still coalescing from the disk of gas and dust that surrounded our infant star. This ice has been preserved in the deep freeze of space ever since, only occasionally being warmed when the comet's orbit brings it close to the sun. When we see a comet's tail, we're watching ancient ice sublimate into gas, releasing molecules that have been locked away since before Earth existed. It's like opening a time capsule that's been sealed for billions of years. Some of that ice might even be older than our solar system. Recent studies of cometary composition have found isotope ratios that suggest some of the material in comets formed in the interstellar medium, the vast spaces between stars before our sun was born. This means that when we observe a comet, we're potentially seeing material that has travelled not just through time, but through space, from other stellar systems, carrying information about conditions in our galaxy billions of years ago. Every comet is a messenger from the deep past, and we're just learning how to read the messages they carry. The possibility that ancient astronomers might have observed and recorded earlier appearances of the comet family that includes 3I Atlas adds a human dimension to this cosmic timeline. If true, it would mean that humans have been unknowingly tracking the same family of objects for millennia, building up a record that spans dozens of generations. Each observation would be a snapshot in time, showing not just the comet but the state of human knowledge and culture at that moment. The Babylonian astronomer recording a wild sheep in the sky, the Chinese astronomer noting a guest star, the medieval European chronicler describing a sign from God, all might have been seeing the same phenomenon, just interpreted through different cultural lenses. This brings us to an interesting question about the nature of scientific progress. We often think of scientific knowledge as accumulating linearly, each generation building on the discoveries of the previous one. But the story of cometary observations suggests a more complex picture. Knowledge can be lost and rediscovered. Observations can be made and forgotten. Patterns can be noticed and then overlooked for centuries. The ancient Greeks knew that Earth was round and had even calculated its circumference with remarkable accuracy, but this knowledge was disputed and partially forgotten during parts of the Middle Ages. Similarly, ancient observations of comets might contain information that we're only now able to appreciate and interpret. The river of time carries knowledge as well as physical objects, but unlike comets, which follow predictable orbits, knowledge can eddy and swirl, flowing backward and forward, disappearing underground only to resurface later. The Library of Alexandria, which might have contained detailed astronomical observations from across the ancient world, was destroyed, taking with it irreplaceable records. The Mayan codices, which contained centuries of astronomical observations, were mostly burned by Spanish conquistadors. How many cometary observations, how many recognized patterns, how many nascent theories were lost in these and other cultural catastrophes? Yet some knowledge survived, preserved in stone, in remaining texts, in oral traditions, in the very architecture of ancient observatories. And now, with our modern tools and understanding, we're trying to piece together these fragments to reconstruct the history of human observation of the cosmos. It's like trying to assemble a vast jigsaw puzzle where most of the pieces are missing, the picture on the box is faded, and we're not even sure all the remaining pieces are from the same puzzle. But occasionally we find a piece that fits perfectly, that connects two previously unconnected sections, that reveals a pattern we hadn't noticed before. The search for connections between 3I Atlas and ancient observations is part of this larger effort to reconstruct our observational history. It requires not just astronomical knowledge, but also historical, linguistic, and cultural understanding. When an ancient text mentions a celestial phenomenon, we need to understand not just what was seen, but how it was interpreted, how it was recorded, what cultural significance it held. A comet that we would describe in terms of orbital elements and chemical composition might have been described by ancient observers in terms of its resemblance to animals, its significance as an omen, or its relationship to earthly events. This multidisciplinary approach to understanding ancient observations has led to some remarkable discoveries. For example, Chinese records of guest stars have been correlated with known supernovae, helping us date these cosmic explosions and understand their frequency. Descriptions of unusual darkening of the sun have been matched with volcanic eruptions that threw ash into the atmosphere. And yes, some ancient cometary observations have been matched with known periodic comets, helping us extend their observational history back centuries or even millennia. The case of 3I Atlas is particularly intriguing because it involves not just a single comet, but potentially a family of related objects. If ancient astronomers observed earlier fragments of this family, they might not have recognized them as related. To them, each would have been a unique event, a separate visitor from the heavens. It's only with our modern understanding of orbital dynamics and cometary fragmentation that we can see the potential connections. We're like detectives finding fingerprints at different crime scenes and realizing they all come from members of the same family. As we drift along this river of cosmic time, carried by the gentle current of contemplation, we begin to see how everything is connected. The ice that formed in the early solar system becomes a comet. The comet fragments into multiple objects. These objects return at different times and are observed by different civilizations. And all of these observations contribute to our growing understanding of the cosmos. We're all part of the same story, the same flow of matter and energy and information through time. The night continues around us, peaceful and vast. Somewhere above, even if we can't see them through our ceiling, the stars continue their ancient patterns. Planets trace their predictable paths. And somewhere in the outer darkness, other cometary fragments continue their long, slow falls toward the sun. Some we'll see in our lifetimes, others won't return for centuries. But they're all part of the same cosmic clockwork, the same grand dance that has been going on since long before humans existed, and will continue long after we're gone. This perspective, this cosmic view of time, can be deeply calming. Whatever concerns brought you to bed tonight, whatever deadlines or pressures you're facing, they're all part of your immediate experience, your personal now. But you're also part of this larger flow, this river that has been flowing for billions of years. The atoms in your body have been on incredible journeys, formed in stars, scattered through space, incorporated into planets, cycled through countless organisms, and now, for this brief moment, assembled into you. You're a temporary arrangement of ancient matter, a brief eddy in the cosmic river, but you're also the river becoming aware of itself. The story of 3 Atlas reminds us that we're all connected across time. The ancient astronomer who might have seen an earlier fragment of this comet family was looking at the same sky we look at, wondering the same things we wonder about, trying to understand their place in the cosmos just as we try to understand ours. They didn't have our instruments or our theories, but they had the same curiosity, the same capacity for wonder, the same desire to make sense of the lights in the sky. In a very real sense, we're continuing their work, adding our observations to theirs, building on the foundation they laid. As we prepare to transition into a closer examination of 3I Atlas itself, its discovery, its characteristics, its journey through our solar system, we're carrying with us this sense of deep time, this awareness of our place in the cosmic river. The specific details of this one comet will make more sense when seen against this vast backdrop, just as a single note makes more sense when heard as part of a symphony. The comet's brief appearance in our skies in 2020 was just one moment in its long history, and our observation of it was just one moment in the long history of human astronomy. But what a moment it was. In the next chapter, we'll explore how modern astronomers first spotted this faint visitor, how they calculated its orbit and realized its potential connection to the Great Comet of 1844, and how they watched in fascination and perhaps a little disappointment as it fragmented before it could put on the spectacular show some had predicted. We'll delve into the science of what makes a comet bright or faint, what causes them to fragment, and what we can learn from their composition. And we'll consider how this one small comet, barely visible even in telescopes, has opened a window into the deep history of our solar system and the possible connections between modern astronomy and ancient observation. The river of time flows on, carrying us toward that exploration. There's no need to paddle or swim. The current will take us where we need to go. Just float, drift. Let the cosmic perspective wash over you like gentle starlight. The universe has been patient for billions of years. It can wait while you rest, while you process these ideas, while you prepare for the next stage of our journey. The comet that was 3I Atlas has already completed its performance, breaking apart and fading from view, but its story continues in the data it left behind, in the questions it raised, in the connections it suggested between past and present, between ancient observers and modern scientists, between the vast cosmos and our small but significant place within it. Time moves differently here in the quiet darkness of contemplation. Minutes might feel like hours, or hours like minutes. That's perfectly fine. We're operating on cosmic time now, where a human lifetime is just a brief flicker, where centuries pass like days, where the patient accumulation of observations across generations slowly builds into understanding. Rest in this timelessness, this sense of being part of something infinitely larger than yourself, yet intimately connected to everything around you. You're stardust contemplating stars, a temporary arrangement of matter that has existed since the beginning of time and will exist until time itself ends. Let's draw closer to our mysterious visitor, the comet 3I Atlas. Picture yourself now not as an observer on Earth, but as a companion to this cosmic wanderer, floating alongside it in the vast darkness beyond Neptune. It's quiet here, so quiet that the very concept of sound becomes meaningless. The sun, which looms so large in our earthly sky, is just the brightest star among many, giving barely more light than a full moon does to Earth. The comet beside you doesn't look like the bright-tailed object we might imagine. Instead, it's a dark, irregular chunk of ice and rock, perhaps a few miles across, tumbling slowly through the void. It's been out here for centuries, following its long elliptical orbit, and it's only now beginning its long fall toward the inner solar system. This is how 3I Atlas spent most of its existence, not as a bright comet, but as a dark, frozen wanderer in the outer reaches of our solar system. For hundreds of years, it drifted through this cosmic wilderness, too faint to be seen from Earth, even if anyone had known where to look. The ice that makes up much of its body has been frozen solid, locked in a crystalline embrace that has lasted since the solar system was young. Embedded in this ice are grains of dust, complex organic molecules, and perhaps secrets about the conditions that existed when the planets were forming. It's a time capsule, but one that can only be opened by the heat of the sun. The discovery of 3I Atlas on December 28, 2019, was in many ways a triumph of modern technology and systematic observation. The Atlas system, which found it, consists of 4 telescopes, 2 in Hawaii, 1 in South Africa, and 1 in Chile, that scan the sky every night, looking for objects that move against the background stars. The system was actually designed to find potentially hazardous asteroids, rocks that might one day collide with Earth, but it's also excellent at discovering comets in the outer solar system. On that December night, the telescopes captured images of a faint, fuzzy object moving slowly through the constellation of Ursa Major. The computers flagged it as interesting, human astronomers confirmed it was a comet, and 3I Atlas entered our consciousness. At first, it seemed like it might become a spectacular sight. Early calculations of its orbit suggested it would pass relatively close to the Sun, and measurements of how it was brightening as it approached suggested it might become visible to the naked eye by May 2020. Some optimistic predictions even suggested it might become as bright as Venus, creating a spectacular sight in the evening sky. The media picked up on these predictions, and for a brief moment 3I Atlas became famous, the comet that would provide a celestial spectacle during a difficult time for humanity. People began planning observation parties, photographers prepared their equipment, and amateur astronomers marked their calendars. But comets, as we have learned time and time again, are unpredictable. They've been called dirty snowballs or icy dirt balls, depending on their composition, and like snowballs, they can be fragile. As 3I Atlas continued its approach to the Sun, astronomers noticed something concerning. Instead of brightening steadily as expected, the comet's brightness began to fluctuate. It would brighten for a few days, then fade, then brighten again. This erratic behavior suggested that something was happening to the comet's nucleus, the solid body at its heart. By late March 2020, it was clear what was happening. 3I Atlas was falling apart. Images from larger telescopes showed that the comet's nucleus had fragmented into multiple pieces, Instead of a single solid body, there were now several chunks, each surrounded by its own cloud of gas and dust. The fragmentation continued through April, with the pieces becoming smaller and fainter. By May, when the comet should have been at its brightest, it had largely dissipated, visible only to large telescopes as a diffuse cloud of debris. The great celestial show that many had hoped for would not materialize. The fragmentation of 3I Atlas was disappointing for those hoping for a bright comet, but it was scientifically fascinating. Watching a comet disintegrate in real time provided valuable data about the structure and composition of these objects. The fragmentation pattern suggested that the comet was held together very loosely, perhaps more like a rubble pile than a solid rock. This fits with our understanding of how comets form in the outer solar system, where low gravity and cold temperatures allow ice and dust to accumulate gradually without compressing into a dense body. The timing of the fragmentation was also interesting. It began when the comet was still about 1.5 astronomical units from the Sun, roughly the distance of Mars' orbit. This is relatively far from the Sun for a comet to begin breaking apart, suggesting that 3I Atlas was particularly fragile. Perhaps it had been weakened by previous passes through the inner solar system, or perhaps it was simply a loose aggregation of material that couldn't withstand even moderate solar heating. The exact cause of the fragmentation remains a subject of scientific debate. As astronomers studied the fragments of 3I Atlas, they noticed something intriguing. The pieces weren't all the same. Some were producing more gas than others, suggesting different compositions. Some were moving slightly faster or slower than others, indicating different masses or different reactions to solar radiation pressure. It was as if the comet had been a poorly mixed cake, with different ingredients clumped together rather than uniformly distributed. This heterogeneity tells us something important about how comets form. They're not uniform objects, but collections of different materials that happen to come together in the early solar system. The connection between 3I Atlas and the Great Comet of 1844 became clearer as astronomers refined their orbital calculations. Both comets followed very similar paths, with orbital periods around 600 years. The slight differences in their orbits could be explained if they were fragments of a larger comet that broke apart sometime in the past, perhaps during a previous passage through the inner solar system. This parent comet would have been substantially larger than either fragment, possibly large enough to be a truly spectacular sight when it appeared in ancient skies. The Great Comet of 1844 itself was a remarkable object. It was discovered on December 18, 1844, by several observers almost simultaneously, a testament to how bright it was even when first spotted. By early 1845, it had developed a tail that stretched across much of the sky, visible even from light-polluted cities. Newspapers of the time were filled with accounts of the comet, mixing scientific observation with religious interpretation and popular speculation. Some saw it as a sign of impending doom, others as a herald of change, and still others simply as a beautiful celestial phenomenon to be enjoyed. The scientific observations of the 1844 comet were quite sophisticated for the time. Astronomers measured its position carefully, calculated its orbit, and even attempted to analyze its light using early spectroscopes. They noted that it seemed to be producing vast amounts of gas and dust, creating not just one tail but multiple tails pointing in slightly different directions. They observed changes in its brightness and structure from night to night, sometimes even from hour to hour. All of this data has proven valuable for modern astronomers trying to understand the relationship between the 1844 comet and 3I Atlas. If these two comets are indeed fragments of the same parent body, it raises interesting questions about what other fragments might be out there. Cometary fragmentation doesn't usually produce just two pieces. It often creates dozens or even hundreds of fragments of various sizes. Some of these might be too small to be detected until they come very close to Earth. Others might be on slightly different orbits that bring them back at different times. There could be a whole family of comets, all related to 3I Atlas and the 1844 comet, waiting to be discovered. This idea of cometary families is supported by other examples we've observed. The Kreutz sungrazers are a family of comets that all follow very similar orbits, passing extremely close to the Sun. They're believed to be fragments of a single enormous comet that broke apart centuries or millennia ago. We see members of this family regularly, sometimes several in a single year. Similarly, the Jupiter family comets, which have orbits influenced by Jupiter's gravity, show clustering that suggests common origins. The comet family that includes 3I Atlas might be another such group, just one that we're only beginning to recognize. The fragmentation of 3I Atlas also provided an opportunity to study the interior of a comet, something that's usually hidden from view. As the comet broke apart, it exposed fresh surfaces that hadn't been altered by solar radiation. The gas and dust released from these fresh surfaces had slightly different compositions than what had been coming from the original surface, suggesting that comets have a kind of geological structure, with different layers or regions containing different materials. This is consistent with models of cometary formation that suggest they built up gradually from smaller pieces, each potentially with its own unique composition. The organic molecules detected in the gas released by 3I Atlas are particularly interesting. Comets are known to contain complex organic compounds, including amino acids, the building blocks of proteins. Some scientists believe that comets might have delivered these organic molecules to early Earth, potentially playing a role in the origin of life. Every comet we study adds to our understanding of what kinds of organic chemistry can occur in the cold, radiation-bathed environment of space. 3I Atlas, despite its fragmentation, contributed its own data to this growing body of knowledge. The disappointment many felt when 3I Atlas failed to become a bright naked-eye comet is understandable, but it's also part of the long history of cometary observation. Comets have always been unpredictable, sometimes exceeding expectations, sometimes failing to live up to them. Comet Kohoutek in 1973 was hyped as the comet of the century, but proved to be a disappointment for casual observers. On the other hand, Comet Hale-Bopp in 1997 exceeded expectations, remaining visible to the naked eye for a record 18 months. This unpredictability is part of what makes comets so fascinating. They remind us that despite all our scientific knowledge, nature can still surprise us. The way different cultures around the world responded to the news of 3I Atlas reveals something about our modern relationship with astronomical phenomena. In an age where we can predict eclipses to the second and track planets with incredible precision, comets remain wildcards. They connect us to a time when the night sky was full of mystery and wonder, when celestial events could inspire fear or joy, when humans looked up and saw not just lights but signs, messages, and stories. Even though we now understand the physics of comets, they still evoke that ancient sense of wonder. The scientific instruments that observed 3I Atlas were far beyond anything ancient astronomers could have imagined. The Hubble Space Telescope, orbiting above Earth's atmosphere, captured detailed images of the fragmentation. Radio telescopes detected specific molecules in the comet's gas cloud. Infrared telescopes measured the heat radiating from the comet's dust. Each type of observation revealed different aspects of the comet's nature, building up a comprehensive picture that no single instrument could have provided. This multi-wavelength approach to astronomy is one of the great advances of modern science, allowing us to see the universe in ways our eyes never could. Yet for all our technological sophistication, we still missed predicting the comet's fragmentation. This humbling reminder of the limits of our knowledge is actually valuable for science. It tells us that our models of cometary structure need refinement, that there are factors we're not fully accounting for, that nature still has lessons to teach us. Every failed prediction is an opportunity to learn, to improve our understanding, to ask better questions. In this way, 3I Atlas's fragmentation might ultimately teach us more than if it had behaved exactly as expected. The dust released by 3I Atlas's fragmentation will continue to orbit the Sun for years, possibly decades. Some of it will eventually fall into the Sun, some will be blown out of the solar system by solar radiation pressure, and some will continue to orbit in a diffuse cloud. If Earth passes through this dust cloud in the future, we might see meteors, tiny pieces of 3I Atlas burning up in our atmosphere. These would be faint meteors, probably not visible to the naked eye, but detectable by sensitive cameras. In this way, the comet's legacy will continue long after the main body is dissipated. The story of 3I Atlas also highlights the importance of continuous sky monitoring. If the Atlas system hadn't been operating, if it hadn't been scanning that particular part of the sky on that December night, we might have missed the comet entirely. It would have approached the Sun, fragmented and dissipated without human witness. How many comets have done exactly that throughout history? How many celestial events have occurred unseen, unrecorded, unknown? The universe doesn't perform for us. It simply is, and we're fortunate when we happen to be watching at the right time. This brings us back to the question of ancient observations. If earlier fragments of the 3I Atlas family appeared in ancient skies, were they seen? Were they recorded? And if they were recorded, can we recognize those records for what they are? The fragmentation of 3I Atlas suggests that any earlier fragments might also have been prone to breaking apart, potentially creating multiple comets from a single approach. Ancient observers might have seen what they thought were several different comets over a period of months, not realizing they were watching the death throes of a single object. The Chinese astronomical records are particularly valuable in this search because of their systematic nature and long duration. Chinese astronomers recorded not just the appearance of comets, but also their paths through the constellations, their changes in brightness, and their duration of visibility. They even noted the color of comets, describing some as white, others as red or blue. These details can help modern astronomers work backward, calculating possible orbits and looking for patterns. The challenge is that the ancient descriptions are often poetic rather than precise, using terms like sweeping star or long star that could refer to different types of phenomena. The Babylonian astronomical texts, written in cuneiform on clay tablets, present different challenges. Many of the tablets are broken or damaged, providing only fragmentary information. The Babylonians used a different coordinate system than we do, based on the zodiac rather than celestial coordinates, which makes it harder to precisely identify what they were observing, and their observations were often mixed with astrological interpretations, making it difficult to separate observational fact from religious or political meaning. Still, when a tablet mentions a hairy star appearing in a certain zodiacal sign at a certain time, it's worth investigating whether this could correspond to a known or suspected comet. Medieval European records add another layer to this detective work. Monks and chroniclers often recorded unusual celestial events, seeing them as signs from God or portents of earthly events. The Anglo-Saxon Chronicle, for instance, famously records the appearance of Halley's Comet in 1066, just before the Norman conquest of England. But it also records other cometary appearances that haven't been definitively matched with known comets. Could one of these be an earlier appearance of a fragment from the 3I Atlas family? The dating in medieval chronicles can be uncertain, and the descriptions are often more concerned with the comet's supposed meaning than its actual appearance, but they still provide valuable data points. Islamic astronomers of the medieval period were perhaps the most scientific in their approach. Building on Greek and Persian traditions while adding their own innovations, they developed sophisticated instruments for measuring celestial positions and created detailed star catalogues. Their observations of comets included not just their paths, but also attempts to measure their distances and sizes. Some Islamic astronomers even proposed that comets were celestial rather than atmospheric phenomena, a view that wouldn't become widely accepted in Europe until centuries later. Their records, written in Arabic and Persian, are still being translated and studied, potentially holding clues to cometary appearances that haven't yet been recognized. The possibility that 3I Atlas was part of a comet family that has been returning for millennia raises profound questions about the relationship between human history and cosmic events. Did the appearance of bright comets influence historical events? Did they inspire religious movements, trigger political changes, or influence cultural development? It's impossible to prove direct causation, but the correlation between cometary appearances and significant historical events is intriguing. The appearance of Halley's Comet has coincided with numerous historical turning points, from the destruction of the Temple in Jerusalem to the Norman conquest to the birth of Mark Twain. Is this just coincidence? Or is there something about the appearance of a bright comet that catalyzes human action? As we contemplate these questions, lying here in the darkness, we're participating in the same activity that has occupied humans since the dawn of consciousness, trying to understand our place in the cosmos. The specific comet we're discussing, 3I Atlas, was just one of countless comets that have visited our skies, and not even a particularly impressive one. But through its connection to the Great Comet of 1844 and the possibility of even earlier appearances, it links us to observers across centuries, to people who looked up at the night sky with the same mixture of wonder and curiosity that we feel today. The fragmentation and dissipation of 3I Atlas might seem like an ending, but in the cosmic perspective, it's just a transformation. The materials that made up the comet, the ice, the dust, the organic molecules, still exist. They've just been dispersed, spread out through the inner solar system. Some of that material will eventually fall to Earth as microscopic meteors, adding their ancient cargo to our planet's inventory. Some will fall into the sun, their atoms joining the solar furnace. Some will be blown out to interstellar space, perhaps to be incorporated into future solar systems billions of years from now. Nothing is truly lost. It just changes form and continues its journey through space and time. This perspective can be deeply comforting as we prepare for sleep. We too are temporary arrangements of ancient matter, destined eventually to disperse and transform. But while we're here, while we maintain this particular configuration of atoms and consciousness, we have the remarkable ability to observe, to wonder, to understand. We can look at a comet and see not just a fuzzy light in the sky, but a messenger from the early solar system, a link to ancient observers, a reminder of our cosmic heritage. We can use the tools of science to unravel its mysteries while still maintaining the sense of awe that our ancestors felt. The story of 3I Atlas is also a reminder of the importance of patience in astronomy. The comet's orbital period of roughly 600 years means that no single human will see it complete even one orbit. Our observations are necessarily fragmentary, catching brief glimpses of processes that unfold over centuries and millennia. This requires us to work together across generations, each adding their observations to the collective record, trusting that future astronomers will continue the work we've begun. It's a humbling reminder that science is a collective enterprise, larger than any individual, extending across time as well as space. As we've explored the story of this one comet, we've touched on themes that resonate throughout astronomy, and indeed throughout human experience. The relationship between expectation and reality, the balance between predictability and surprise, the connection between past and present, the transformation of matter and energy, the accumulation of knowledge across generations. These themes will continue to weave through our story as we delve deeper into the science of cometary orbits, the records of ancient astronomers, and the philosophical implications of our cosmic connections. The night continues its quiet progression around us. Perhaps you can hear the subtle sounds of your home settling, the distant hum of civilization, the rhythm of your own breathing. These immediate, present-moment experiences are no less real, no less important than the cosmic scales we've been contemplating. You exist simultaneously in the here and now, and in the vast sweep of cosmic time. You're both a brief flicker of consciousness and part of an unbroken chain of existence stretching back to the Big Bang. This dual nature, temporal and eternal, finite and infinite, small and significant, is part of what makes human existence so remarkable. As we prepare to transition into exploring the science of cometary orbits, the mathematical poetry that governs how these cosmic wanderers trace their paths through space, remember that you don't need to understand every detail to appreciate the beauty of the story. The equations that describe orbital motion are just one way of expressing the elegant dance that comets perform. Ancient observers who had no knowledge of these equations still recognized the beauty and significance of cometary appearances. They understood, in their own way, that these were special events worthy of attention and recording. The mathematics that governs the movement of comets through space is both elegantly simple and mysteriously complex. As we settle deeper into our exploration, imagine gravity not as a force, but as a gentle curve in the fabric of space itself, like the depression a marble makes when placed on a stretched sheet. The Sun, massive and patient at the center of our solar system, creates the deepest depression, and everything else, planets, asteroids, comets, rolls along the curves this depression creates. This is Einstein's vision of gravity, but even Newton's older conception of gravity as an invisible thread connecting all objects with mass helps us understand the beautiful paths comets trace through space. When we speak of a comet's orbit, we're describing a mathematical relationship between the comet and the Sun, a dance choreographed by the laws of physics that have operated unchanged since the universe began. The orbit of 3i Atlas, like all cometary orbits, is an ellipse, an oval shape with the Sun at one focus. But this simple description hides layers of complexity. The ellipse isn't perfect. It's perturbed by the gravity of planets, especially Jupiter, that massive shepherd of the outer solar system. It's affected by non-gravitational forces too, the pressure of sunlight, the reaction force from gas jetting off the comet's surface, even the subtle effects of relativity. Each of these influences is tiny, but over centuries they add up, slowly reshaping the comet's path through space. To understand how scientists connected 3i Atlas to the Great Comet of 1844, we need to appreciate the detective work involved in orbital determination. When astronomers first spot a comet, they know only its position in the sky at that moment. From a single observation, the comet could be anywhere along a line extending from Earth out into space. It could be close and slow-moving, or distant and fast. It takes multiple observations over days or weeks to begin constraining its orbit. As data accumulates, computers run millions of possible orbital solutions, gradually narrowing down the possibilities until they converge on the most likely path. The process is like trying to determine the shape of a railroad track by glimpsing the train through scattered windows as it passes. Each observation provides a position, and, by comparing positions over time, a velocity. But comets don't follow simple circular paths like trains on tracks. Their elliptical orbits can be extremely elongated, taking them from the outer darkness beyond Neptune to scorching proximity to the Sun. Some comets have orbits so elongated that they're barely bound to the Sun at all, visiting once and then escaping to interstellar space. Others, like Halley's Comet, return regularly, their orbits shaped by repeated encounters with planets. The orbital period of a comet, the time it takes to complete one full orbit, depends on the size of its ellipse. This relationship was discovered by Johannes Kepler in the early 1600s and is now known as Kepler's third law. The larger the orbit, the longer the period, but not in a simple linear relationship. A comet with an orbit twice as large doesn't take twice as long to orbit. It takes nearly 3 times as long. This mathematical relationship means that comets from the outer solar system, like 3i Atlas, spend most of their time moving slowly through the cold darkness, and only brief periods racing through the inner solar system where we can observe them. The similarity between the orbits of 3i Atlas and the Great Comet of 1844 was noticed almost immediately after 3i Atlas's orbit was determined. Both comets followed paths inclined at nearly the same angle to the plane of Earth's orbit. Both had similar orbital periods, around 600 years. Both reached their closest approach to the Sun, their perihelion, at nearly the same distance. These similarities were too precise to be coincidental. The probability of two unrelated comets having such similar orbits is vanishingly small. The most likely explanation was that both comets were fragments of a larger parent body that had broken apart sometime in the past. But when did this fragmentation occur? Here the detective work becomes even more complex. If the parent comet broke apart recently, say in the last few orbits, the fragments would still be travelling close together, perhaps arriving within years or decades of each other. But 3 Atlas and the 1844 comet arrived 176 years apart, suggesting the fragmentation happened longer ago. By analysing the slight differences in their orbits and working backward, astronomers estimated that the fragmentation might have occurred during a previous passage through the inner solar system, perhaps around the 13th or 14th century, or even earlier. This is where the connection to ancient observations becomes tantalizing. If a large comet fragmented in, say, 1200 CE, it might have been a spectacular sight, bright enough to be seen in daylight, impossible to ignore, and indeed, Chinese records from 1222 describe a remarkable comet that was visible for months. Could this have been the parent comet of 3I Atlas and the 1844 comet in the process of breaking apart? The dates don't match exactly, but given the uncertainties in orbital calculations and the possibility that the fragmentation occurred over multiple orbits, the connection can't be ruled out. The forces that cause comets to fragment are varied and not fully understood. Tidal forces from the Sun can tear apart comets that pass too close, as happened spectacularly with comet Shoemaker-Levy 9 when it passed close to Jupiter. Thermal stress from uneven heating can crack the nucleus, especially if the comet is rotating and different sides are exposed to sunlight. The pressure from jets of gas can act like rocket engines, pushing fragments apart. Even the subtle pressure of sunlight itself, acting over centuries, can spin up a comet until centrifugal force tears it apart. 3 Atlas seemed to fragment due to thermal stress, breaking apart as it warmed during its approach to the Sun, but the exact mechanism remains uncertain. The concept of orbital families extends beyond just 3 Atlas and the 1844 comet. Astronomers have identified several groups of comets with similar orbits, suggesting common origins. The Kreutz sun grazers, mentioned earlier, all follow nearly identical paths that take them extremely close to the Sun. Over 4,000 members of this family have been observed, mostly by space-based solar observatories that can see comets even when they're lost in the Sun's glare. The parent of the Kreutz family must have been enormous, perhaps hundreds of miles across, to produce so many fragments. Some astronomers speculate it might have been one of the great comets observed in antiquity, perhaps the comet of 371 BCE, described by Aristotle, or the comet of 1106 CE, recorded by astronomers around the world. The Jupiter family comets represent a different kind of orbital grouping. These are comets with periods less than 20 years, whose orbits have been shaped by repeated encounters with Jupiter. They didn't necessarily start as fragments of a single comet, but Jupiter's gravity has corralled them into similar orbits. Studying these families helps us understand how planetary gravity sculpts the distribution of small bodies in the solar system. It's a cosmic billiards game, with Jupiter as the dominant player, sending comets careening off in new directions or capturing them into shorter orbits. Understanding cometary orbits also helps us assess potential threats to Earth. While the probability of a comet striking Earth is extremely small, it's not zero. The impact that killed the dinosaurs 66 million years ago might have been a comet rather than an asteroid. Comets are particularly challenging for planetary defense because they can approach from any direction, unlike asteroids which mostly orbit in the same plane as the planets. A long-period comet falling in from the outer solar system might only be discovered months before a potential impact, giving us little time to respond. This is why surveys like Atlas are so important. They give us as much warning as possible of approaching objects. But let's return to the peaceful contemplation of orbital mechanics as a form of cosmic poetry. Each comet's orbit is unique, shaped by its individual history of gravitational encounters. Some orbits are nearly circular, others extremely elongated. Some are prograde, orbiting in the same direction as the planets, others retrograde, moving against the cosmic traffic. Some orbits are stable for millions of years, others chaotic, changing dramatically with each passage. This diversity tells us that the solar system is not a static clockwork mechanism, but a dynamic, evolving system, where chance encounters can dramatically alter destinies. The mathematical tools we use to calculate orbits would have seemed like magic to ancient astronomers. We can take a handful of observations and extrapolate them centuries into the past or future. We can account for the gravitational influence of all the major planets, the subtle effects of relativity, even the pressure of sunlight. Our computers can process millions of orbital solutions in seconds, finding the needle of truth in a haystack of possibilities. Yet for all our computational power, we still can't predict exactly when a comet will fragment or how bright it will become. Nature retains some mysteries even in this age of mathematical precision. The connection between mathematics and the physical world is one of the deep mysteries of science. Why should abstract mathematical concepts developed in the human mind so perfectly describe the motion of celestial bodies? Why do ellipses discovered by Greek geometers studying conic sections turn out to be the shapes of planetary orbits? Why does the inverse square law of gravitation, a simple mathematical relationship, govern the motion of everything from falling apples to orbiting galaxies? These questions touch on the fundamental nature of reality and our ability to comprehend it. Ancient astronomers, lacking our mathematical tools, still recognize patterns in cometary appearances. They noticed that some comets appeared in certain seasons more than others. They observed that comets generally moved from west to east against the background stars, though their paths could be complex. They recognized that comets with certain characteristics, brightness, color, tail length, might portend different earthly events. While we now know these correlations were largely imaginary, the careful observations that supported them were real and valuable. Those ancient astronomers were doing science, even if they didn't call it that. The Babylonians, despite not understanding orbits in our modern sense, developed mathematical methods for predicting celestial events. They discovered that eclipses repeat in cycles, that planets return to the same positions at regular intervals, that the moon's motion follows complex but predictable patterns. They expressed these patterns not in equations but in tables of numbers, elaborate ephemerides that could be used to predict future positions. Some historians of science argue that Babylonian astronomy was more arithmetical than geometrical, more concerned with numerical patterns than physical models. Yet their predictions were remarkably accurate. Greek astronomers added geometry to the Babylonian arithmetic, creating physical models of the cosmos. Apollonius of Perga, the same mathematician who studied conic sections, proposed that planets moved in circles upon circles, epicycles upon deferents, to explain their complex motions. While this model was wrong in detail, it was conceptually sophisticated, recognizing that complex motion could arise from combinations of simple motions. Ptolemy refined this system to achieve remarkable predictive accuracy, creating a model that would dominate astronomy for over 1,000 years. The Islamic astronomers who inherited and developed Greek astronomical knowledge made crucial contributions to our understanding of orbits. They refined observational techniques, developed new mathematical methods, and questioned assumptions that Greek astronomers had taken for granted. Al-Battani improved measurements of the obliquity of Earth's axis and the length of the year. Ibn al-Haytham developed a theory of optical phenomena that helped explain atmospheric effects on astronomical observations. Al-Tusi developed mathematical techniques that Copernicus would later use in his heliocentric model. These contributions laid groundwork for the revolution in orbital understanding that would come with Kepler and Newton. When we trace the orbit of 3I Atlas backward in time, we're using mathematical tools developed over millennia. The equations we solve incorporate insights from Babylonian pattern recognition, Greek geometry, Islamic mathematical innovation, Kepler's laws of planetary motion, Newton's universal gravitation, and Einstein's relativity. Each generation of astronomers built upon the work of their predecessors, refining our understanding of how celestial bodies move through space. The orbit of this one small comet thus connects us not just to ancient observers, but to ancient mathematicians and theorists who developed the tools we still use today. The precision with which we can now calculate orbits is extraordinary. For well-observed comets, we can predict their positions years in advance to within a few miles, across distances of billions of miles. This precision allows us to send spacecraft to rendezvous with comets, as the European Space Agency did with Comet 67P Churyumov-Gerasimenko. The Rosetta mission orbited the comet for 2 years and deployed a lander to its surface, achievements that would have been impossible without precise orbital calculations. Every such mission adds to our understanding of cometary composition and behavior, helping us interpret observations of comets we can only observe from afar. The non-gravitational forces acting on comets add complexity to orbital calculations. As a comet approaches the Sun and begins to heat up, jets of gas and dust erupt from its surface. These jets act like tiny rocket engines, pushing the comet in unexpected directions. The effect is small but cumulative, and over multiple orbits, it can significantly alter a comet's path. This is why the return of periodic comets like Halley can vary by days or even weeks from predictions based solely on gravitational forces. For 3I Atlas, these non-gravitational forces might have contributed to its fragmentation, as uneven heating created stresses that the fragile nucleus couldn't withstand. The pressure of sunlight itself, though incredibly weak, also affects cometary orbits. This radiation pressure is what pushes dust particles away from the comet to form the dust tail, which always points away from the Sun regardless of the comet's direction of motion. For small particles, radiation pressure can overcome solar gravity entirely, blowing them out of the solar system. For the comet nucleus itself, radiation pressure is negligible compared to gravity, but over centuries it can produce measurable changes in the orbit. This effect, called the Yarkovsky effect for asteroids, and the similar Poynting-Robertson effect for dust particles, is another reminder that space is not empty, but filled with subtle influences. As we contemplate these orbital complexities, it's worth remembering that we're not just passive observers, but active participants in the cosmic dance. Earth's gravity, tiny though it is compared to the Sun's, still affects passing comets. Our planet has probably slightly altered the orbits of thousands of comets over geological time. Some comets that might have hit Earth were deflected to safety. Others that would have missed were pulled into collision courses. We're part of the gravitational web that shapes cometary orbits, just as cometary impacts have shaped our planet's history. The search for patterns in cometary orbits continues with ever more sophisticated techniques. Machine learning algorithms now sift through centuries of observations, looking for subtle correlations that human astronomers might miss. Statistical analyses search for clustering in orbital parameters that might indicate common origins. Dynamical simulations run the solar system backward and forward in time, exploring how orbits evolve under various scenarios. Each new discovery adds another piece to our understanding of how comets move through space and time. The orbital connection between 3I Atlas and the Great Comet of 1844 is just one example of how modern astronomy can link observations across centuries. As our computational power increases and our databases of observations grow, we'll likely discover more such connections. Perhaps we'll find that other historic comets were related. The ancient observations correspond to calculated past positions, that patterns exist in cometary appearances that we haven't yet recognized. Each connection we discover is a bridge across time, linking us to observers who looked up at the same phenomena we study today. The philosophical implications of orbital mechanics extend beyond astronomy. The discovery that celestial motions follow mathematical laws contributed to the Enlightenment idea that nature is comprehensible through reason. If the complex dance of planets and comets could be reduced to equations, perhaps other natural phenomena could be similarly understood. This confidence in mathematical description of nature underlies all of modern science. Yet the fragmentation of Three-Eye Atlas reminds us that predictability has limits, that chaos and complexity emerge even in systems governed by simple laws. As you lie there, perhaps feeling the slow rotation of Earth beneath you, you're experiencing orbital motion directly. The gentle cycle of day and night, the progression of seasons, the monthly phases of the moon, all are consequences of orbits. Your body has evolved to these rhythms, your circadian clock synchronized to Earth's rotation, your annual cycles influenced by our orbit around the Sun. In a very real sense, orbital mechanics is encoded in your biology. You're not separate from the cosmic dance, but an integral part of it. The story of cometary orbits also illustrates how science progresses through the interplay of observation and theory. Observations inspire theories, theories make predictions, predictions guide new observations, and unexpected observations force revision of theories. This cycle has been repeating since humans first began trying to understand the lights in the sky. The fragmentation of Three Atlas was unexpected, challenging our theories about cometary structure. The orbital similarity to the 1844 comet was a successful prediction, confirming our understanding of orbital dynamics. Both the success and the failure advance our knowledge. Looking forward, the study of cometary orbits will likely reveal new surprises. As we discover more comets in the outer solar system, we might find orbital patterns that suggest unknown gravitational influences, perhaps a distant, undiscovered planet, or the cumulative effect of passing stars. As we observe more cometary fragmentations, we might discover patterns that help us predict which comets are likely to break apart. As we extend our observations further back in time through historical records, and further forward through improved predictions, we might discover cycles and patterns we haven't imagined. The mathematics of orbits also connects us to the possibility of interstellar visitors. In 2017, astronomers discovered Oumuamua, the first confirmed object from another star system to pass through ours. Its orbit was hyperbolic, meaning it was moving too fast to be bound to our Sun. 2 years later, Comet Borisov became the second confirmed interstellar visitor. These objects remind us that our solar system is not isolated, but part of a galactic community where stars and their attendant comets occasionally visit each other. The orbital calculations that confirmed these objects' interstellar nature were based on the same principles used to study Three-Eye Atlas. As we prepare to explore the world of ancient skywatchers, those patient observers who tracked celestial motions without telescopes or computers, we carry with us this understanding of orbital mechanics. When we read their descriptions of comets appearing in certain constellations, we can calculate whether a member of the Three-Eye Atlas family could have been in that position. When they describe a comet's motion over weeks or months, we can compare it to calculated orbital paths. When they note a comet breaking into pieces, we can consider whether they were witnessing an earlier fragmentation in the same family. The mathematics of orbits becomes a time machine, allowing us to reconstruct what ancient observers might have seen. The precision of modern orbital calculations contrasts sharply with the poetic descriptions of ancient astronomers, yet both approaches capture something essential about comets. The equations tell us where a comet will be, but the ancient descriptions tell us what it means to see one. The calculations predict the comet's brightness, but the historical accounts describe the awe it inspired. We need both perspectives, the quantitative and the qualitative, the mathematical and the mythological, to fully appreciate these cosmic visitors. As we transition into exploring the world of ancient astronomy, we'll see how different cultures developed their own ways of understanding and recording cometary appearances, creating a rich tapestry of observations that we're still trying to interpret today. Long before our telescopes, ancient eyes gazed at the same stars, and in the darkness of those prehistoric nights, humans began the long journey of trying to understand what they saw above them. Picture yourself transported back 5,000 years, standing on a ziggurated platform in ancient Mesopotamia, the cradle of astronomy. The city below is dark, lit only by oil lamps and cooking fires. Above, the sky blazes with stars invisible to modern city dwellers, the Milky Way a bright river across the heavens. You're a priest astronomer, one of a hereditary line that has watched the sky for generations. And tonight, something new has appeared. A fuzzy star with a tail, moving slowly through the constellation you call the Bull of Heaven. The Babylonians were among the first to systematically record celestial events, and their clay tablets, inscribed with cuneiform wedges, provide us with the oldest detailed astronomical observations. They called comets wild sheep stars, seeing in their fuzzy appearance something like the wool of their flocks. But this whimsical name shouldn't fool us into thinking their observations were casual. The Babylonian astronomers maintained careful records spanning centuries, noting the positions of planets, the timing of eclipses, and yes, the appearance of comets. They developed mathematical techniques for predicting celestial events that were remarkably sophisticated, using arithmetic progressions and period relations that wouldn't be improved upon for over 1,000 years. In the ruins of the Royal Library of Ashurbanipal in Nineveh, archaeologists have found thousands of astronomical tablets. Among them are the Enuma Anu Enlil, a series of 70 tablets containing celestial omens collected over centuries. These texts describe various astronomical phenomena and their supposed terrestrial consequences. When they mention a comet, they often describe not just its appearance, but its path through the constellations, its colour, the length and direction of its tail, and how long it remained visible. One tablet from around 1600 BCE describes a comet that rose in the path of Anu, referring to the celestial equator, and set in the path of Ea, the southern sky. Could this have been an ancient appearance of a comet in the Three-Eye Atlas family? The challenge in interpreting these ancient records is that the Babylonians didn't distinguish between different types of celestial phenomena the way we do. A hairy star might be a comet, but it could also be a bright meteor, a nova, or even a close conjunction of planets. The Babylonians were more interested in the astrological significance of these events than in what we would consider their physical nature. To them, a comet was a message from the gods, its appearance timed to coincide with earthly events. If a comet appeared when a king died, it was seen as the cause, not a coincidence. This mixing of observation and interpretation makes it challenging to extract pure observational data from their records. Yet when we strip away the astrological interpretations, we find remarkably accurate observations. The Babylonians noted that comets generally move from west to east against the star background, though their paths could be complex. They observed that some comets were visible for just days while others remained for months. They distinguished between comets with long tails and those with short ones, between bright comets visible in daylight and faint ones barely visible at night. These observations, recorded on tablets that have survived for millennia, provide us with a window into the ancient sky that no other source can match. Moving eastward and forward in time, we encounter the astronomical traditions of ancient China, perhaps the most complete and systematic record of celestial observations in human history. Chinese astronomers were meticulous record keepers, maintaining continuous observations for over 2 millennia. They called comets broom stars, huixing, when they had long tails, or guest stars, qixing, when they appeared more star-like. The Chinese imperial astronomers were government officials, tasked with watching the heavens for signs that might affect the empire. Their observations were state secrets, carefully recorded and preserved in imperial archives. The Chinese astronomical records are particularly valuable because they often provide detailed positional information. Chinese astronomers divided the sky into 28 lunar mansions, sections defined by prominent stars. When they recorded a comet, they would note which mansion it appeared in, how it moved from night to night, and when it disappeared. For example, the records of the Grand Historian by Sima Xian, written around 100 BCE but incorporating much older records, describes dozens of cometary appearances going back centuries. One entry from 613 BCE states, "In autumn, a comet entered the Great Bear constellation. It was visible for more than 40 days. Such specific information allows modern astronomers to attempt orbital calculations, checking whether known comets could have been in those positions at those times. The Chinese also developed theories about comets that were surprisingly sophisticated. While many cultures saw comets as supernatural omens, some Chinese astronomers proposed naturalistic explanations. The astronomer Shi Shen, working in the 4th century BCE, suggested that comets were celestial bodies like planets, but with unusual orbits. This was remarkably prescient, anticipating by 2 millennia the modern understanding of comets as solar system objects. Chinese astronomers also noted correlations between cometary appearances and meteor showers, an observation that wouldn't be fully understood until the 19th century when the connection between comets and meteor streams was established. One of the most intriguing Chinese records that might relate to the Three-Eye Atlas family comes from 1222 CE, the history of song records. In the 8th month, a broom star appeared in the eastern sky. It was as bright as Venus and visible in daylight. Its tail stretched across half the sky. It remained visible for 21 days before fading. The timing is tantalizingly close to when the parent body of Three-Eye Atlas and the 1844 comet might have fragmented. Was this bright comet the progenitor breaking apart? The description of it being visible in daylight suggests an exceptionally bright comet, consistent with a large nucleus that might have produced multiple fragments. The ancient Egyptians, despite their sophisticated civilization and monumental architecture aligned with celestial events, left us fewer direct astronomical records than the Babylonians or Chinese. This might be because they wrote on papyrus, which deteriorates over time rather than clay or stone. However, we do have some tantalizing hints about Egyptian cometary observations. The pyramid texts, carved into the walls of pyramids from around 2400 BCE, contain references to celestial phenomena that might be comets. One passage speaks of a star with hair that swims through the sky, a description that certainly sounds cometary. Egyptian astronomy was closely tied to their religious beliefs and their practical need to predict the annual Nile flood. They developed a sophisticated calendar based on the heliacal rising of Sirius, which coincided with the flood. Any unusual celestial event like a bright comet would have been interpreted in the context of this cosmic order. The few Egyptian astronomical texts that survive, like the Carlsberg Papyrus from the 2nd century CE, show that Egyptian astronomers were capable of sophisticated calculations. They could predict eclipses and planetary positions, suggesting they might also have tracked cometary appearances, even if those records haven't survived. The ancient Greeks brought a different perspective to cometary observations, attempting to understand them through natural philosophy, rather than just recording them as omens. Aristotle, writing in the 4th century BCE, proposed that comets were atmospheric phenomena, dry exhalations from Earth that ignited in the upper atmosphere. This theory, though wrong, was based on observations. Comets didn't show the regular motion of planets. They appeared and disappeared unpredictably, and they seemed to be associated with weather changes. Aristotle's theory would dominate European thinking about comets for nearly 2,000 years. But not all Greek philosophers agreed with Aristotle. The Pythagoreans proposed that comets were planets that only occasionally became visible. Apollonius of Myndus suggested they were celestial bodies with their own orbits. Seneca, the Roman philosopher writing in the 1st century CE, prophetically stated, "The day will come when posterity will be amazed that we remained ignorant of things that will to them seem so plain. The day will yet come when the progress of research through long ages will reveal to sight the mysteries of nature that are now concealed." He was specifically talking about comets when he wrote this, showing remarkable foresight about how scientific understanding progresses. Greek and Roman historians also recorded cometary appearances, often linking them to significant historical events. The comet that appeared after Julius Caesar's assassination in 44 BCE was interpreted as his soul ascending to heaven and became a powerful political symbol. Coins were minted showing the comet, and it was incorporated into the imperial cult. The historian Pliny the Elder, writing in the 1st century CE, attempted to catalogue different types of comets based on their appearance, describing some as bearded, others as javelin-like, and still others as tub-shaped. While his classifications don't match our modern understanding, they show careful observation of cometary diversity. The Mayan astronomers of Central America developed one of the most sophisticated astronomical systems in the ancient world, despite working independently from Old World traditions. The Dresden Codex, one of only 4 Mayan books to survive the Spanish conquest, contains detailed astronomical tables including what appear to be records of cometary observations. The Mayans called comets smoking stars and associated them with the god Kukulkan, the feathered serpent. Their observations were precise enough to predict eclipses accurately, suggesting their cometary records might also be reliable. Mayan astronomy was deeply integrated with their complex calendar system and their religious beliefs. They tracked multiple cycles simultaneously: the 260-day sacred calendar, the 365-day solar calendar, the cycles of Venus and other planets, and possibly the appearances of certain comets. Some researchers have suggested that certain dates in Mayan inscriptions that don't correspond to known astronomical cycles might record cometary appearances. If true, this would give us another independent record of ancient comets that we could compare with observations from other cultures. In ancient India, astronomical observations were recorded in Sanskrit texts that blend scientific observation with religious and mythological interpretation. The Vedas, composed between 1500 and 500 BCE, contain references to celestial phenomena that might include comets. Later texts like the Surya Siddhanta and the Aryabhatiya show sophisticated understanding of planetary motion and eclipse prediction. Indian astronomers called comets Dhumaketu, literally smoke banner, recognizing their fuzzy extended appearance. The Indian astronomical tradition is particularly interesting because it developed sophisticated mathematical techniques independently from but parallel to Greek astronomy. Indian astronomers used trigonometry and algebraic methods to calculate celestial positions, and they understood concepts like the precession of equinoxes. The astronomer Varahamihira, writing in the 6th century CE, described various types of comets and their supposed effects, mixing careful observation with astrological interpretation. He noted that comets could appear in any part of the sky, move in various directions, and last for different durations. All accurate observations despite the astrological framework. The Islamic astronomers of the medieval period inherited and synthesized astronomical knowledge from Greek, Indian, Persian, and other traditions, creating the most advanced astronomy of their time. They established observatories from Spain to Central Asia, developed new instruments like the astrolabe and the equatorium, and made observations of unprecedented accuracy. Islamic astronomers were particularly interested in testing and refining Greek astronomical theories, and their observations of comets played a role in this process. Abd al-Rahman al-Sufi, writing in the 10th century, created a star catalogue that updated Ptolemy's ancient catalogue with new observations. He also recorded several cometary appearances, describing their paths through the constellations, with enough detail that modern astronomers have been able to identify some of them with known periodic comets. The astronomer Ibn al-Haytham challenged Aristotle's theory that comets were atmospheric phenomena, arguing based on parallax observations that they must be more distant than the Moon. This was a crucial insight that wouldn't be widely accepted in Europe for centuries. The medieval European chroniclers, mainly monks and clerics, continued the tradition of recording unusual celestial events, though often with more emphasis on their supposed meaning than their actual appearance. The Anglo-Saxon Chronicle, maintained in various versions from the 9th to 12th centuries, records several cometary appearances. The most famous is the entry for 1066. Then was seen over all England such a portent as no man ever before saw. Some men said it was the star comet, which some men call the haired star. This was Halley's comet, which appeared just before the Norman conquest and is famously depicted in the Bayeux Tapestry. Medieval European observations are valuable because they provide independent confirmation of cometary appearances recorded in Chinese and Islamic sources. When multiple cultures on different continents record a bright comet at the same time, we can be confident the observation is real. The challenge is that medieval European descriptions are often vague, more concerned with the comet's supposed significance than its actual position or motion. A typical entry might read, "A comet appeared in the north, presaging war and famine," without providing enough detail to identify which comet it was or calculate its orbit. The possibility that ancient observers recorded earlier appearances of the Three-Eye Atlas family becomes more plausible when we consider the global nature of these observations. If a bright comet appeared in, say, 600 CE, it might have been recorded by Chinese imperial astronomers, Islamic scholars in Baghdad, Mayan priests in Central America, and European monks. Each would have described it differently, interpreted it through their own cultural lens, but the underlying phenomenon would be the same. By comparing these independent records, we might be able to identify candidates for earlier appearances of our cometary family. The ancient observers we've been discussing operated under a fundamental disadvantage. They could only see comets when they were bright enough to be visible to the naked eye. This means they missed the vast majority of comets that pass through the inner solar system. A comet like Three-Eye Atlas, which never became brighter than magnitude 8, would have been completely invisible to them. Only if earlier fragments were substantially larger and brighter would they have been recorded. This selection bias means that ancient records are weighted toward great comets, the spectacular visitors that everyone could see. Yet this limitation also means that when ancient observers did record a comet, it was likely significant. They weren't distracted by the dozens of faint comets that modern telescopes reveal. Every comet they recorded was bright enough to be seen without optical aid, which means it was either relatively large, relatively close to Earth, or both. This makes ancient cometary records particularly valuable for understanding the population of large comets and how it might have changed over time. The interpretation of ancient astronomical texts requires collaboration between astronomers, historians, linguists, and archaeologists. A single word's translation can make the difference between identifying a comet and missing it entirely. Cultural context is crucial. What might seem like a fanciful description to us might have been a technical term to ancient observers. Dating is often uncertain, with different calendar systems and copying errors introducing ambiguity. Yet despite these challenges, patient scholarship has extracted remarkable astronomical information from ancient texts. Modern computational tools have revolutionized the study of ancient astronomy. We can now calculate the positions of stars and planets for any date in the past, accounting for precession and other long-term changes. This allows us to check ancient observations against calculated positions, validating some records and questioning others. We can run orbital integrations backward for centuries, seeing where known comets would have appeared in ancient skies. And we can search for patterns in ancient observations that might have been invisible to the observers themselves. The question of whether Three-Eye Atlas was predicted in ancient texts thus becomes part of a larger investigation into the history of cometary observation. Even if we can't definitively link specific ancient observations to the Three-Eye Atlas family, the search itself teaches us about how astronomical knowledge developed, how different cultures understood celestial phenomena, and how patient observation over generations can reveal patterns invisible to any single observer. The ancient skywatchers we've been discussing were our predecessors in the quest to understand the cosmos, and their observations, however interpreted through myth and superstition, represent humanity's first attempts at systematic astronomy. As you lie there in the darkness, perhaps you can imagine yourself as one of these ancient observers. The comet you're watching moves so slowly that its motion is barely perceptible from night to night. You make careful notes of its position relative to familiar stars, its brightness, the length and direction of its tail. You consult the records of your predecessors, looking for similar appearances in the past. You wonder what this celestial visitor means, where it comes from, where it's going. You don't have our modern understanding of orbits and gravity, but you have something we've largely lost, an intimate nightly familiarity with the sky, born from years of patient observation. The tradition these ancient observers began continues today. When modern astronomers tracked 3-eye atlas, they were adding to a record that stretches back millennia. The instruments have changed, from naked eye to telescope to CCD camera, but the fundamental activity remains the same: watching the sky, recording what we see, looking for patterns, trying to understand. Every observation, whether recorded on a clay tablet in ancient Babylon or in a digital database today, contributes to humanity's growing understanding of the cosmos. The ancient observations we've been exploring also remind us that astronomy has always been a multicultural enterprise. No single civilization had a monopoly on sky watching. Chinese astronomers recorded comets that European observers missed. Islamic astronomers preserved Greek knowledge that would have otherwise been lost. Mayan astronomers developed calendrical calculations that rivaled anything in the Old World. This diversity of perspectives enriched astronomical knowledge, providing multiple independent records of celestial events and different theoretical frameworks for understanding them. The possibility that ancient observers saw earlier fragments of the 3-eye atlas family adds a temporal dimension to this cultural diversity. If true, it means that observers separated by centuries and continents were unknowingly watching the same extended family of objects, each seeing a different member at a different time. The Babylonian priest astronomer recording a wild sheep star in 1600 BCE, the Chinese court astronomer noting a broom star in 600 CE, the medieval European monk describing a hairy star in 1200 CE, all might have been observing fragments of the same original comet, contributing pieces to a puzzle that we're only now beginning to assemble. This perspective transforms ancient astronomical texts from historical curiosities into scientific data. Every carefully recorded observation, no matter how wrapped in mythology or superstition, potentially contains information about the real cosmos. The challenge is extracting that information, separating observation from interpretation, accounting for different calendar systems and observational techniques, and correlating observations across cultures. It's detective work of the highest order, requiring expertise in multiple fields and patience to work through ambiguous and sometimes contradictory evidence. As we've seen, the ancient observers who might have witnessed earlier appearances of comets in the 3-eye atlas family were far from primitive. They were sophisticated observers working within their technological limitations, developing theories and making predictions, building a body of knowledge that would eventually evolve into modern astronomy. They watched the same sky we watch, wondered at the same phenomena we study, and asked many of the same questions we're still trying to answer. Their observations, preserved in clay, stone, papyrus and tradition, connect us across millennia to the dawn of astronomical observation. The story of ancient cometary observation also illustrates how knowledge can be lost and rediscovered. The Greek understanding that Earth orbits the Sun, proposed by Aristarchus in the 3rd century BCE, was forgotten for over a millennium. Chinese observations of sunspots, recorded for centuries, were unknown to European astronomers who independently discovered them with telescopes. How many cometary observations, how many recognized patterns, how many theoretical insights were lost to war, disaster, or simple neglect? And what might we be overlooking in our modern observations that future astronomers will recognize as significant? As we prepare to explore the specific connection between 3 Atlas and the Great Comet of 1844, we carry with us this rich heritage of ancient observation, the possibility that both comets are fragments of something seen by ancient astronomers adds depth to their story. They're not just isolated events, but part of a continuing narrative that spans human history. Every bright comet that appears in our skies connects us to this tradition, reminding us that we're part of a conversation about the cosmos that began when humans first looked up in wonder and will continue as long as eyes turn skyward. The Great Comet of 1844 appeared at a fascinating moment in the history of astronomy, when ancient traditions of observation were giving way to modern scientific methods. Photography was in its infancy, spectroscopy was just being developed, and the true nature of comets was still debated. The comet would be observed by both traditional naked-eye observers and astronomers using the latest telescopic technology, creating a bridge between old and new ways of studying the cosmos. Its possible connection to 3-Eye Atlas adds another layer to this bridge, potentially linking observations across centuries. Picture the evening of December 18th, 1844, in Cape Town, South Africa. The astronomer Thomas McClure, working at the Royal Observatory, noticed something unusual in his telescope, a fuzzy object that hadn't been there the night before. Within days, independent discoveries were reported from Australia, South America, and ships at sea. The comet was brightening rapidly, already visible to the naked eye, its tail beginning to stretch across the southern sky. News of the discovery spread via sailing ships and the newly invented telegraph, reaching European and North American observatories weeks later. By then, the comet had become a spectacular sight, visible even from gaslit city streets. The Great Comet of 1844, officially designated C1844Y1, would become one of the most observed comets of the 19th century. At its peak in January 1845, it rivaled Venus in brightness, its tail stretching across nearly a third of the sky. Observers described it in breathless terms: a celestial searchlight, God's own lantern, a sword of fire hanging over the Earth. The comet was visible from both hemispheres, though southern hemisphere observers had the best views. Ships' logs from vessels sailing the southern oceans provide some of the most detailed observations, as sailors had unobstructed views and plenty of time to watch the comet's nightly progression. The timing of the comet's appearance was significant for the development of astronomy. The 1840s were a period of rapid advancement in astronomical instrumentation and theory. The planet Neptune would be discovered just 2 years later, in 1846, based on mathematical predictions. The nature of the Milky Way as a collection of stars was being revealed by improved telescopes. The first astronomical photographs were being attempted, though exposure times were still too long to capture a moving comet. Scientists were beginning to understand that the universe was far larger and older than previously imagined. Professional astronomers around the world turned their instruments toward the comet. At the Paris Observatory, François Arago attempted to analyze the comet's light using a polariscope, trying to determine whether the tail was self-luminous or merely reflecting sunlight. At the Harvard College Observatory, William Cranch Bond used the newly installed Great Refractor, then one of the largest telescopes in the world, to study the comet's nucleus. He reported seeing multiple condensations within the coma, possibly early signs of fragmentation that would only become apparent to later analysts. The orbital calculations for the 1844 comet were performed by some of the greatest mathematical astronomers of the age: Johann Franz Encke in Berlin, Urbain Le Verrier in Paris, and John Couch Adams in Cambridge all computed orbits independently. Their calculations showed that the comet was on a highly elliptical orbit, with a period of several centuries. The exact period was uncertain. Estimates ranged from 500 to 700 years, because the observations only covered a small portion of the orbit near perihelion. This uncertainty would prove significant when astronomers later tried to link the comet to historical appearances. What makes the 1844 comet particularly interesting for our story is the detailed descriptions of its physical appearance and behavior. Multiple observers reported that the comet seemed to be shedding material unevenly, with jets or fountains of gas appearing to erupt from specific points on the nucleus. The tail showed complex structure, with multiple streamers and what appeared to be disconnection events, where portions of the tail separated from the comet and drifted away. Some observers reported changes in the comet's brightness over periods of hours, suggesting active processes on the nucleus. The comet's spectrum, though crude by modern standards, was observed by several astronomers using early spectroscopes. They reported bright emission lines that we now know indicate the presence of various gases, carbon compounds, water vapor, and other volatiles being released from the warming ice. The strength of these emissions suggested that the comet was rich in volatile materials, consistent with an origin in the cold outer solar system. This spectroscopic evidence would later prove valuable in establishing the connection to 3I Atlas, which showed similar spectral features during its approach. Public reaction to the 1844 comet was intense and varied. In Europe and America, it inspired poetry, paintings, and musical compositions. The comet appears in the backgrounds of several paintings from 1845, often as a symbol of divine presence or cosmic mystery. Religious leaders interpreted it variously as a sign of coming judgment, a call to repentance, or a reminder of God's glory. Scientists gave public lectures trying to explain the comet's nature and reassure people that it posed no danger to Earth. Newspapers published daily updates on the comet's position and appearance, making it perhaps the first celestial event to receive modern media coverage. In China, the comet was recorded in the official astronomical records of the Qing dynasty. Chinese astronomers called it the Great Broom Star of the Daoguang era and tracked it for 47 days. Their observations, recorded in classical Chinese, provide an independent data set that modern astronomers have used to refine the comet's orbital calculations. The Chinese records are particularly valuable because they include observations from when the comet was fading, after Western observers had largely stopped tracking it. The possible fragmentation of the 1844 comet, suggested by Bond's observation of multiple condensations in the coma, takes on new significance in light of 3I Atlas. If the 1844 comet was already showing signs of breaking apart, it would explain why 3I Atlas was so fragile when it returned. Each passage near the Sun stresses a comet's nucleus through thermal cycling and tidal forces. A comet that survives one passage might be weakened enough to fragment on the next. This progressive deterioration could mean that what was once a single, massive comet has been breaking into smaller pieces over multiple orbits. The connection between the 1844 comet and 3I Atlas was first suggested by amateur astronomer Mike Meyer in April 2020, while 3I Atlas was still approaching the Sun. Meyer noticed that the orbital elements of the two comets were remarkably similar, nearly identical inclinations, arguments of perihelion, and longitudes of ascending node. The main difference was in the orbital period, but this could be explained by non-gravitational forces acting differently on different size fragments. Professional astronomers quickly confirmed Meyer's discovery, running detailed orbital simulations that showed the two comets could indeed be fragments of the same parent body. If we accept that the 1844 comet and 3I Atlas are related, we can work backward to estimate when their parent body might have been visible. Assuming a roughly 600-year orbital period and accounting for uncertainties, the parent comet might have appeared around 12 to 44 CE, give or take a few decades. This immediately sends us searching through medieval records for bright comets around that time, and indeed we find intriguing candidates. Chinese records mention a bright comet in 1264, visible for several months. European chronicles describe a terrible comet in 1240 that was interpreted as heralding the Mongol invasions. Could one of these have been the parent body in the process of fragmenting? The physical characteristics of both the 1844 comet and 3I Atlas provide clues about their parent body. Both were rich in volatile ices, suggesting formation in the cold outer solar system. Both showed similar spectral features, indicating similar composition. The 1844 comet was much brighter than 3I Atlas, suggesting it was a larger fragment, while 3I Atlas's rapid fragmentation suggests it might have been a smaller, weaker piece. If we imagine a parent comet breaking into multiple fragments of different sizes, we'd expect to see exactly this pattern. Larger fragments appearing as great comets, smaller ones as fainter objects, some perhaps too small to detect at all. The story becomes even more intriguing when we consider that there might be other fragments still out there. Cometary fragmentation rarely produces just two pieces. When comet Shoemaker-Levy 9 broke apart, it created at least 21 fragments. When comet Linear fragmented in 2000, dozens of pieces were observed. If the parent of the 1844 comet and 3I Atlas underwent a similar fragmentation, there could be many other pieces on similar orbits, returning at slightly different times. Some might have already passed through the inner solar system unnoticed. Others might be approaching, years or decades from discovery. This raises the tantalizing possibility that some historical comets, previously thought to be unrelated, might actually be members of the same family. The Great Comet of 1264, mentioned in Chinese records, had an orbit that some researchers suggest could be consistent with the 3I Atlas family. The comet of 1695, observed by Cassini and Flamsteed, showed orbital similarities that might not be coincidental. Even some ancient comets, recorded only in fragmentary texts, might be earlier appearances of this extended family. Each potential connection requires careful analysis, accounting for orbital evolution, non-gravitational forces, and the uncertainties in historical observations. The 1844 comet also provides a baseline for understanding how comets evolve over successive passages. By comparing detailed observations from 1844 with what we saw of 3I Atlas in 2020, we can infer how fragmentation and sublimation change a comet over time. The 1844 comet was estimated to be several kilometers across. 3I Atlas was probably less than a kilometer. This size difference, if both are fragments of the same parent, tells us something about the fragmentation process and how material is distributed among the pieces. The cultural impact of the 1844 comet extended beyond its immediate appearance. It inspired a generation of amateur astronomers to take up comet hunting, leading to a golden age of cometary discovery in the late 19th century. It prompted improvements in telescopic equipment and observational techniques. It contributed to the growing public interest in astronomy that would culminate in the founding of numerous public observatories and astronomical societies. In many ways, the 1844 comet helped establish astronomy as both a professional science and a popular pursuit. The comet also played a role in developing our understanding of cometary physics. The detailed observations of its tail structure led to theories about how solar radiation shapes cometary tails. The changes in its brightness prompted investigations into how comets produce light. The spectroscopic observations, primitive though they were, began the process of understanding cometary composition that continues today. Every great comet advances our knowledge, and the 1844 comet, appearing when it did at a crucial time in astronomical history, contributed more than most. The possibility that ancient astronomers observed the parent body of the 1844 comet and 3I Atlas adds a deep historical dimension to these scientific investigations. If a great comet appeared around 1244 CE and was seen fragmenting, it would have been interpreted very differently by different cultures. European observers, living in an age of crusades and conquests, might have seen it as a sign of divine judgment. Chinese astronomers, working within a tradition that saw comets as indicators of celestial imbalance, would have carefully recorded its appearance for the imperial archives. Islamic astronomers, at the height of their scientific achievements, might have attempted to measure its distance and understand its nature. Working backward even further, if the parent body had appeared around 644 CE, it would have been visible during the early expansion of Islam, the height of the Tang dynasty in China, and the depths of the Dark Ages in Europe. Each culture would have observed and interpreted it through their own lens, creating a diverse record that we can only partially reconstruct. The comet itself, indifferent to human affairs, would have continued its orbit, slowly fragmenting over successive passages, creating the family of objects we're only now beginning to recognize. The search for historical appearances of this cometary family illustrates how modern astronomy builds on centuries of observation. Every recorded comet, from ancient Chinese records to 19th century European observations to modern CCD images, adds to our understanding. The 1844 comet, observed with the best technology of its time, provides a crucial link between ancient naked-eye observations and modern telescopic studies. It was bright enough to be seen and recorded by casual observers, but also studied with sufficient scientific rigor to determine its orbit accurately. As we lie here contemplating these connections across time, we're reminded that astronomy is fundamentally about pattern recognition. The pattern that connects 3I Atlas to the 1844 comet, and possibly to earlier historical comets, emerged only when we had enough data points and sophisticated enough analysis tools. Ancient astronomers might have suspected that some comets were related. Chinese astronomers noted that certain comets seemed to appear at regular intervals, but they lacked the mathematical framework to prove it. We stand on their shoulders, using their observations combined with our modern understanding to see patterns they could only guess at. The fragmentation of 3I Atlas in 2020, disappointing as it was for observers hoping for a bright comet, actually strengthens the connection to the 1844 comet. Both objects showed signs of structural weakness. Both were shedding material actively. Both were rich in volatiles that would sublime vigorously when heated by the sun. These similarities suggest not just a common origin, but a common fate. Progressive fragmentation over multiple orbits, until nothing remains but a stream of dust and small particles. This is how comets die. Not in a single dramatic event, but through gradual disintegration over millennia. The story of the 1844 comet and its possible connection to 3I Atlas also reminds us of the role of serendipity in astronomical discovery. Meyer wasn't looking for connections when he noticed the orbital similarities. He was simply comparing orbital elements out of curiosity. The original discoverers of both comets weren't expecting to find fragments of an ancient parent body. They were conducting routine observations. Science often advances through such unexpected connections, when someone notices a pattern that others have overlooked or makes a link between seemingly unrelated phenomena. As our exploration continues, we see how the Great Comet of 1844 serves as a bridge between ancient observation and modern understanding. It was observed by some of the last great naked-eye astronomers and some of the first to use photography and spectroscopy. It appeared when orbital calculations were becoming precise enough to look for historical connections, but before we fully understood cometary physics. It was bright enough to inspire public wonder, but studied with enough scientific rigor to provide solid data. In many ways, it was the perfect comet to create a link between past and present, between 3I Atlas and whatever ancient parent body spawned them both. The question of whether this cometary family was predicted in ancient texts becomes more complex and interesting when we consider the 1844 comet. If ancient astronomers saw the parent body, they might have recorded not just its appearance but its fragmentation. They might have noted multiple comets appearing in succession, not realizing they were pieces of the same object. They might have tried to find patterns in these appearances, creating the first tentative predictions of cometary returns. The 1844 comet and 3 Atlas might be just the most recent chapters in a story that began when humans first started recording what they saw in the night sky. As we prepare to search for deeper patterns in these cometary appearances, to look for the cosmic cycles that might connect observations across millennia, we carry with us the image of the Great Comet of 1844 stretching across the sky, observed by millions, recorded by hundreds, analysed by the greatest astronomers of the age. It was a moment when humanity's ancient practice of comet watching met the emerging science of astrophysics, when wonder and analysis combined to advance our understanding of these cosmic visitors. The comet itself, unconscious of its role in human history, continued on its orbit, slowly deteriorating, preparing to return centuries later as the fragment we called 3I Atlas, continuing a story that connects us all to the cosmos and to each other across the vast river of time. In the quiet expanse of data, we search for gentle patterns, and perhaps nowhere is this search more compelling than in the quest to understand whether the appearances of comets, like 3I Atlas, and its celestial siblings follow some deeper rhythm, some cosmic cycle that our ancestors might have intuited even without our modern tools. Consider this possibility as you rest there in the darkness. What if the universe operates like a vast musical instrument, with comets as notes that repeat in complex harmonies we're only beginning to hear? The search for these patterns isn't just about mathematics and orbital mechanics. It's about discovering whether there's an underlying order to what seems random, whether coincidence might actually be cosmic choreography. The human mind is exquisitely tuned to find patterns, sometimes even where none exist. This tendency, called apophenia, has led to both remarkable discoveries and persistent delusions throughout history. When ancient Chinese astronomers noticed that certain comets seemed to return at regular intervals, were they detecting real patterns or imposing order on chaos? When medieval chroniclers linked cometary appearances to earthly events, were they recognizing genuine correlations or creating meaning where none existed? The challenge for modern astronomers is to distinguish between real patterns and statistical coincidences, between cosmic cycles and random clustering. Let's begin with what we know with reasonable certainty. The orbital period of the 3I Atlas family appears to be approximately 600 years, though this number comes with significant uncertainties. Orbital periods aren't fixed constants, but variables that change over time due to planetary perturbations, non-gravitational forces, and the gradual evolution of the solar system itself. Jupiter, that giant gravitational shepherd, can alter a comet's period by years or even decades during a close encounter. The gentle pressure of sunlight, accumulated over centuries, can slowly spiral a comet inward or push it outward. Even the gradual loss of mass as ice sublimes changes a comet's response to these forces. If we accept a roughly 600-year period and work backward from the 1844 comet, we get approximate dates of 1244, 644, 44 CE, 556 BCE, 1156 BCE, and so on. These dates are not precise predictions, but rather windows of possibility, each perhaps spanning several decades. Now comes the detective work. Can we find recorded comets near these dates that might be members of our cosmic family? The answer is tantalizing but frustratingly incomplete. Yes, there are recorded comets near some of these dates, but the uncertainties in both the calculated periods and the historical dates make definitive connections impossible. Chinese records, our most complete historical data set, do indeed show interesting clusters. There was a bright comet in 1264, just 20 years after our calculated date of 1244. Another appeared in 676, 32 years after our estimate of 644. Going further back, we find comets recorded in 147 CE, about a century after our predicted 44 CE. Are these discrepancies too large to indicate a real connection, or are they within the range of uncertainty given orbital evolution and dating errors? The question remains open, inviting us to consider what level of evidence we require to move from speculation to probability. The search for patterns becomes even more intriguing when we consider that the 3 Atlas family might be just one of many cometary families returning on various cycles. Some researchers have proposed that bright comets appear in waves, with certain periods seeing more great comets than others. Statistical analysis of historical records shows some evidence for this clustering, though whether it represents real physical patterns or random variation is debated. If cometary families tend to fragment at certain orbital locations, perhaps due to resonances with planetary orbits, we might expect to see multiple fragments returning within relatively short periods, creating these apparent waves. Consider the decade of the 1840s, which saw not just the Great Comet of 1844 but also the Great March Comet of 1843, one of the brightest comets in recorded history. Were these related? The 1843 comet was a Kreutz sun grazer with a completely different orbit from the 1844 comet, so they weren't fragments of the same immediate parent. But could there be deeper connections, perhaps involving the gravitational focusing effects of the outer planets that send multiple comets into the inner solar system at around the same time? Or is this just coincidence, the kind of random clustering that appears in any dataset if you look hard enough? The mathematical tools we use to search for patterns have become increasingly sophisticated. Fourier analysis can detect periodic signals buried in noisy data. Wavelet transforms can identify patterns that change over time. Machine learning algorithms can find correlations that human analysts might miss. When these tools are applied to the historical record of cometary appearances, they do find suggestions of periodicity, but the signals are weak and the noise is strong. The historical record is too incomplete, too biased toward bright comets, too corrupted by dating uncertainties and observational gaps to provide definitive answers. Yet perhaps we're looking for the wrong kind of patterns. Instead of searching for strict periodicity, maybe we should be looking for evolutionary patterns, ways in which cometary families change over time. Each passage near the Sun alters a comet slightly, changing its orbit, its mass, its structure. Over many passages, these changes accumulate, potentially creating predictable evolutionary sequences. A large comet might fragment into medium-sized pieces, which further fragment into smaller pieces, which eventually dissipate into meteor streams. If we understood these evolutionary patterns better, we might be able to work backward from current observations to reconstruct the history of cometary families. The concept of orbital resonances adds another layer to pattern searching. Resonances occur when orbital periods form simple ratios, like 2.1 or 3.2. Objects in resonance experience repeated gravitational interactions at the same orbital positions, which can either stabilize or destabilize their orbits. Some cometary families might be locked in resonances with Jupiter or other planets, creating patterns in their returns that aren't strictly periodic but follow more complex cycles. The mathematics of resonances, developed through the study of planetary rings and asteroid belts, might apply to cometary families as well. The search for patterns also extends to the physical characteristics of comets. Do members of the same family share similar compositions? Do they fragment in similar ways? Do they show similar activity patterns as they approach the Sun? The limited data we have suggests that family members do share characteristics, but the sample size is small and the observations are often incomplete. 3I Atlas and the 1844 comet showed some similar features. Both were rich in carbon compounds. Both showed evidence of fragmentation, but whether these similarities are family traits or common to many comets remains uncertain. Ancient astronomers, working without our mathematical tools, might have detected patterns through different means. They had something we lack: cultural continuity over centuries or millennia. Chinese astronomical records were maintained continuously for over 2,000 years. Babylonian astronomical traditions were passed down through generations of priest astronomers. These long baselines of observation might have revealed patterns that we, with our much shorter scientific tradition, haven't yet recognized. When a Chinese astronomer noted that a comet resembled one recorded by his predecessors centuries earlier, was he recognizing a family resemblance we've lost the ability to see? The role of human perception in pattern recognition cannot be ignored. We see faces in clouds, animals in constellations, significance in coincidence. This pattern-seeking behavior, evolutionarily advantageous for survival, can lead us astray in scientific analysis. The history of astronomy is littered with perceived patterns that turned out to be illusory. The Martian canals, the supposed correlation between planetary positions and earthquakes, the belief that comets directly cause plagues and wars. Yet this same pattern-seeking drive has led to genuine discoveries: the recognition of planetary retrograde motion, the discovery of stellar parallax, the identification of periodic comets. Modern statistical methods help us distinguish between real patterns and random noise, but they're not infallible. A pattern that appears significant in one statistical test might disappear in another. The choice of analysis method, the way data is binned or smoothed, the treatment of uncertainties, all can affect whether patterns appear or vanish. This is why the search for patterns in cometary appearances remains contentious, with different researchers reaching different conclusions from the same data. It's a reminder that science is not just about data, but about interpretation, and interpretation is always influenced by assumptions and expectations. The possibility of cosmic cycles extends beyond just orbital periods. Some researchers have proposed that the solar system periodically passes through regions of the galaxy with higher densities of interstellar material, potentially triggering increased cometary activity. Others suggest that the Sun might have a distant, undiscovered companion star whose gravitational influence periodically disturbs the Oort cloud, sending showers of comets into the inner solar system. These hypotheses, while speculative, illustrate how the search for patterns can lead to new theoretical frameworks and testable predictions. The fragmentation patterns of comets might themselves follow predictable cycles. As a comet repeatedly passes near the Sun, thermal stresses create fractures that grow with each passage. At some critical point, the accumulated damage causes fragmentation. If we understood these processes better, we might be able to predict not just when a comet will return, but when it will fragment, creating new members of its family. The fragmentation of 3I Atlas in 22P might have been predictable if we had better models of cometary structure and better data on its previous passages. Climate records on Earth provide another dataset to search for patterns. Some researchers have proposed that cometary impacts or airbursts might leave signatures in ice cores, tree rings, or sediment layers. If cometary families return on predictable cycles and occasionally produce Earth-impacting fragments, we might find periodic signals in these terrestrial records. The Younger Dryas cooling event 12,900 years ago has been linked by some researchers to a cometary impact, though this remains highly controversial. If true, it might be part of a pattern of periodic impacts that we haven't yet recognized. The search for patterns isn't just about the past, it's about prediction. If we can identify genuine cycles in cometary appearances, we can forecast future events. Will other fragments of the 3I Atlas family appear in coming decades? Are we approaching a period of increased cometary activity, or a quiet phase? These aren't just academic questions. A bright comet can inspire public interest in astronomy, while a potentially hazardous object requires planetary defense preparations. Understanding patterns helps us prepare for both opportunities and threats. The philosophical implications of finding or not finding patterns are profound. If cometary appearances follow predictable cycles, it suggests a cosmos more ordered than chaotic, more deterministic than random. It would vindicate, in a sense, the ancient belief that celestial events follow divine or natural laws that can be discovered through careful observation. On the other hand, if cometary appearances are truly random, it emphasizes the role of chance in cosmic events, and perhaps in the development of life on Earth. Since comets might have delivered water and organic molecules to our young planet. As you lie there, perhaps feeling your own breathing settle into a rhythm, you're experiencing pattern at the most fundamental level. Your heartbeat, your breath, your circadian rhythms, all are patterns that connect you to larger cosmic cycles. The Earth rotates, creating day and night. It orbits the Sun, creating seasons. The Moon orbits Earth, creating tides. These nested cycles influence all life on Earth, from the simplest bacteria to human civilizations. We evolved in a universe of patterns, and our brains are wired to detect and respond to them. The search for patterns in cometary appearances is thus part of a larger human quest to understand our place in the cosmos. Are we living in a clockwork universe where everything follows predictable laws, or a chaotic system where randomness reigns? The answer, as quantum mechanics and chaos theory have taught us, is probably both. The universe follows laws, but those laws can produce unpredictable outcomes. Patterns exist, but they're often hidden in noise, visible only through patient observation and careful analysis. The story of 3i Atlas and its possible family illustrates this duality perfectly. The orbital mechanics that govern its motion are deterministic, following Newton's and Einstein's laws with exquisite precision. Yet the comet's fragmentation was unpredictable, a chaotic event triggered by complex internal processes we don't fully understand. The comet's return was a pattern fulfilled. Its dissolution was randomness asserting itself. Both aspects are real, both are important, and both contribute to the cosmic story we're trying to read. Consider how different cultures have interpreted patterns in cometary appearances. To ancient Chinese astronomers, comets were disruptions in the celestial harmony, signs that the emperor had lost the mandate of heaven. They looked for patterns linking cometary appearances to dynastic changes, and given the long history of Chinese civilization, they often found them. Were these real correlations or confirmation bias? Perhaps both. Political instability might lead to neglect of astronomical observations, creating gaps that make patterns harder to detect. Or perhaps the appearance of a bright comet, interpreted as a bad omen, might actually trigger political upheaval through psychological effects. Medieval European chroniclers saw patterns linking comets to plagues, wars, and the deaths of kings. The Black Death of the 14th century was preceded by several cometary appearances, a correlation that seemed to confirm comets as harbingers of disaster. Modern analysis shows no causal connection, but the psychological impact was real. People who expected disaster after seeing a comet might behave in ways that made disaster more likely, creating a self-fulfilling prophecy. These social patterns, while not cosmic in origin, are still patterns worth understanding. Islamic astronomers took a different approach, trying to find mathematical patterns in cometary motions without necessarily linking them to earthly events. They developed sophisticated geometric models and computational techniques, looking for underlying order in apparent chaos. Their work, preserved in manuscripts from Baghdad to Cordoba, shows a systematic attempt to move beyond superstition toward scientific understanding. They didn't always succeed, but their methods laid groundwork for later discoveries. The modern search for patterns benefits from vast computational power and large data sets, but it also faces unique challenges. Light pollution has disconnected most people from the night sky, breaking the chain of continuous observation that ancient cultures maintained. Our scientific tradition, while powerful, is only a few centuries old, a brief moment compared to the millennia over which cometary patterns might unfold. We have better tools but less patience, more data but less cultural continuity. Perhaps the patterns we seek require both modern analysis and ancient wisdom to fully understand. The question of whether 3i Atlas was predicted in ancient texts thus becomes part of this larger investigation into pattern and meaning. Even if we can't definitively say that ancient astronomers predicted this specific comet, the search itself reveals patterns in how humans observe, record, and interpret celestial events. Every culture that recorded comets was contributing to a pattern of observation that continues today. Every astronomer who calculated an orbit was adding to a pattern of increasing precision. Every person who looked up at a comet and wondered about its meaning was participating in a pattern of cosmic curiosity that defines our species. As we move deeper into the 21st century, new technologies promise to revolutionize pattern detection in astronomy. The Vera Rubin Observatory, with its ability to survey the entire visible sky every few nights, will detect far more comets than ever before, providing the statistical power to identify subtle patterns. Machine learning algorithms will sift through this data, potentially finding correlations no human would notice. Space-based telescopes will observe comets throughout their orbits, not just during their brief appearances in the inner solar system. Yet technology alone won't answer our questions about patterns and predictions. We also need theoretical frameworks to interpret what we observe. Why do comets fragment when they do? How do orbital families evolve over time? What role does chaos play in determining which patterns persist and which dissolve? These questions require not just observation but understanding, not just data but theory. The patterns we seek might be hiding not in the data itself but in the relationships between different types of data, in the connections between orbital dynamics and physical properties, between ancient observations and modern physics. The story of 3i Atlas reminds us that patterns can be broken as easily as they're made. Whatever pattern its orbital family might have been following was disrupted when it fragmented in 2020. Future returns of family members will follow different patterns, influenced by the redistribution of mass and momentum during the fragmentation event. This is how patterns evolve in a dynamic universe, through constant creation and destruction, formation and dissolution, order emerging from chaos only to dissolve back into it. Perhaps the most important pattern is the one we're creating right now, the pattern of human beings trying to understand their cosmic environment. Every observation of 3i Atlas, every calculation of its orbit, every speculation about its history adds to this pattern. We're weaving a tapestry of knowledge that future generations will continue, adding their own observations and insights. The pattern isn't just in the comets themselves, but in our ongoing effort to understand them. As you rest there in the quiet darkness, you might sense patterns all around you. The rhythm of your breathing, the distant hum of civilization, the slow wheeling of stars overhead, even if you can't see them through your ceiling. These patterns connect you to the cosmos in ways both obvious and subtle. You're made of atoms forged in stars, arranged in patterns encoded in DNA, thinking thoughts that follow patterns laid down by evolution and culture. You're a pattern recognizer in a universe full of patterns, some real, some imagined, all part of the great mystery we're trying to solve. The search for patterns in cometary appearances will continue long after 3 Atlas has faded from memory. Future astronomers will have better tools, more complete data, deeper theoretical understanding. They might definitively answer questions we can only speculate about. They might discover that what we thought were patterns were just coincidences, or that what we dismissed as random was actually part of a deeper order we couldn't perceive. The search itself is a pattern, a rhythm of question and answer, mystery and discovery that beats at the heart of science. What does a visiting comet teach us about our own lives? This question invites us into a philosophical reverie as gentle as starlight, as profound as the spaces between galaxies. As you lie there in the darkness, perhaps already drifting towards sleep, consider how the story of 3i Atlas mirrors the fundamental truths of existence itself. Here was an object that travelled for centuries through the cold darkness, ancient beyond human comprehension, carrying within its frozen heart materials that formed when our solar system was young. It approached the sun, began to warm and transform, showed signs of vibrant activity, and then, just when observers expected it to bloom into full glory, it fell apart, dissolving into fragments that continued on separate paths. Is this not, in its way, a perfect metaphor for life itself? The long preparation, the brief flowering, the inevitable dissolution, and the continuation of essence in new forms. The impermanence that 3i Atlas embodied so dramatically is not a flaw in the cosmic design, but perhaps its most essential feature. Everything in the universe is temporary, from the briefest quantum fluctuation to the longest-lived stars. Galaxies collide and merge, stars are born and die, planets form and are destroyed, and comets fragment and disperse. Yet this constant change, this cosmic impermanence, is precisely what makes existence dynamic and creative. Without change, without endings and beginnings, the universe would be static, frozen, essentially dead. The fragmentation of 3i Atlas wasn't a failure, but a transformation. Not an ending, but a redistribution of ancient materials that will eventually become part of new cosmic structures. Consider the paradox of identity that comets present to us. Was 3I Atlas the same object that began its journey in the Oort cloud millions of years ago? As it approached the Sun, it lost tremendous amounts of material to sublimation, its very substance streaming away in its magnificent tail. By the time it fragmented, it had already transformed substantially from whatever it once was. And if it was a fragment of a larger parent body that broke apart centuries ago, when did it become 3I Atlas rather than part of something else? These questions mirror philosophical puzzles about human identity. Are you the same person you were as a child, despite every atom in your body having been replaced multiple times? What persists through change, and what makes something itself rather than something else? The fleeting nature of 3I Atlas's visibility speaks to how much of the universe's activity occurs beyond our perception. The comet spent roughly 599 years and 11 months of its 600-year orbit in darkness, too faint to see even with telescopes, carrying out its cosmic journey in solitude. Only for a few weeks was it bright enough for us to observe, and even then, it required instruments to detect. How much of existence unfolds this way, in spaces and times we cannot witness? Every moment, countless cosmic dramas play out beyond our perception. Stars exploding in distant galaxies, planets forming around alien suns, perhaps other civilizations rising and falling on worlds we'll never know. Our observations, precious as they are, capture only the tiniest fraction of cosmic activity. This hidden nature of most cosmic activity invites humility about our place in the universe. We tend to think of ourselves as central to the cosmic story, but comets like 3I Atlas remind us that the universe doesn't perform for us. It simply unfolds according to its own patterns and processes, indifferent to whether we're watching. The comet didn't fragment to disappoint eager observers. It fragmented because internal stresses exceeded structural strength. This cosmic indifference might seem cold, but it can also be liberating. We're free to find our own meaning, create our own significance, without the burden of cosmic judgment or expectation. Yet there's another perspective that emerges from contemplating 3I Atlas, one that emphasizes connection rather than separation. The comet was made of the same elements we are: hydrogen, oxygen, carbon, nitrogen, just arranged differently and existing in different conditions. The water ice in the comet was chemically identical to the water in our bodies. The organic molecules detected in its spectrum were cousins to the molecules that make up our DNA and proteins. When we observed 3I Atlas, we were quite literally watching our extended family, distant cousins in the great genealogy of matter that connects everything in the solar system. This material connection extends to causation as well. Comets like 3I Atlas might have delivered water and organic molecules to early Earth, contributing to the conditions that allowed life to emerge. Every comet that passes through the inner solar system sheds dust that eventually falls to Earth as micrometeorites, adding extraterrestrial material to our planet. We breathe atoms that were once in comets, drink water that might have travelled aboard these icy wanderers, are built from materials that have circulated through the solar system for billions of years. The boundary between us and the cosmos isn't as clear as it might seem. We're not separate from space, but part of it. Temporary arrangements of cosmic material that has existed since the beginning and will exist until the end. The timescales involved in the story of 3I Atlas offer another philosophical lesson. The comet's 600-year orbit means that no human sees it twice. The astronomers who observed it in 2020 were different from those who saw the Great Comet of 1844, who were different from whoever might have seen earlier appearances. Yet through written records and scientific knowledge, we create a kind of institutional memory that transcends individual lifetimes. We know about the 1844 comet not through direct experience, but through the observations of people long dead, preserved in documents and data. This transmission of knowledge across generations is perhaps humanity's greatest achievement, allowing us to accumulate understanding beyond what any individual could achieve. The fragmentation of 3I Atlas also speaks to the relationship between fragility and resilience. The comet was fragile enough to break apart from solar heating, yet its fragments continue on their orbits, each now a comet in its own right. What seemed like destruction was actually multiplication. Where there was one object, now there are many. This pattern appears throughout nature. A seed must break open for a plant to grow, a cell must divide for an organism to develop, a star must die for heavy elements to be dispersed. Fragility and resilience aren't opposites, but partners in the cosmic dance of transformation. The way different people responded to 3I Atlas's fragmentation reveals something about human nature and our relationship with expectations. Some were disappointed that the predicted bright comet failed to materialize. Others were excited by the rare opportunity to watch a comet fragment in real time. Scientists saw it as a valuable source of data about cometary structure. Philosophers might see it as a reminder that the universe doesn't conform to our expectations. Each perspective is valid, each adds something to our collective understanding. The comet itself, of course, was neither success nor failure. It simply was what it was, following the laws of physics without regard for human categories. There's a beautiful paradox in how we relate to objects like 3I Atlas. On one hand, we study them scientifically, reducing them to orbital elements, chemical compositions, and physical processes. On the other hand, we can't help but see them poetically, mythologically, as symbols and metaphors for human experiences. Neither perspective is complete without the other. The scientific view without the poetic lacks meaning. The poetic view without the scientific lacks grounding. When we combine both perspectives, we get something richer than either alone, a view that acknowledges both the mechanical and the meaningful, the physical and the philosophical. The question of consciousness adds another layer to our philosophical contemplation. Was 3 Atlas aware in any sense? Almost certainly not in any way we would recognize. Yet it responded to its environment, warming in sunlight, cooling in darkness, fragmenting under stress. It had a kind of agency, following its path not passively, but through constant interaction with gravitational and other forces. This raises questions about the nature of consciousness and experience. Where exactly does mere physical response end and awareness begin? We don't know, and comets like 3I Atlas remind us how much mystery remains in questions we thought we understood. The story of 3I Atlas also illustrates the role of chance in cosmic events, and perhaps in our own existence. If the comet had been slightly larger or smaller, had a slightly different composition, or approached the sun at a slightly different angle, it might not have fragmented. It might have become the bright naked-eye comet many hoped for, or it might have remained too faint to generate much public interest. These small differences, amplified by chaotic dynamics, lead to vastly different outcomes. The same is true in our own lives. Small chances and choices, minor variations in timing or circumstance, can lead to completely different life trajectories. Yet within this chance, patterns emerge. 3I Atlas followed the same laws of physics that govern all matter. Its fragmentation, while unpredictable in detail, followed patterns we've observed in other comets. This interplay between determinism and chaos, between law and chance, seems to be fundamental to how the universe operates. Perfect predictability would eliminate novelty. Complete randomness would prevent the emergence of complex structures. The universe we inhabit exists in the sweet spot between these extremes, where laws provide structure but chance provides creativity. The way we name and categorize comets reveals something about human psychology. 3I Atlas is a technical designation that tells us when and how it was discovered, but it lacks poetry, personality, meaning. The Great Comet of 1844 is more evocative but still defines the object by its relationship to human observation. Ancient names like Bearded Star or Broom Star were more descriptive, more immediate. Each naming convention reflects the culture that created it, the values and perspectives of the namers. The comet itself, indifferent to what we call it, continues on its path regardless. As we contemplate the philosophical implications of 3i Atlas, we might wonder what lessons it offers for how we live our lives. Perhaps it teaches us to embrace both planning and adaptability, to chart our course like a comet following its orbit, but be ready to transform when conditions change. Perhaps it reminds us that spectacular visibility isn't the only measure of significance. 3i Atlas contributed valuable scientific data despite never becoming bright. Perhaps it shows us that endings can be beginnings, that fragmentation can be a form of multiplication, that apparent failure can be actual transformation. The comet also offers a meditation on attention and observation. How many comets pass through our skies unnoticed? How many moments of beauty and significance do we miss because we're not watching? 3i Atlas was visible for only a brief time to those who knew where to look and had the right equipment. It makes us wonder what else might be passing by, literally or metaphorically, that we're not equipped or positioned to perceive. This isn't cause for anxiety, but for wonder. The universe is full of activity, full of stories unfolding, whether we witness them or not. The relationship between expectation and reality that 3i Atlas embodied so clearly is a fundamental aspect of human experience. We constantly project our hopes and fears onto future events, imagining how things will unfold, often being surprised when reality differs from our imagination. The comet was going to be spectacular, the comet of the decade, visible to the naked eye until it wasn't. This gap between expectation and reality can be disappointing, but it can also be instructive. It reminds us that the universe has its own agenda, its own patterns and processes that don't necessarily align with our desires. Yet there's beauty in this misalignment. If everything went according to our expectations, there would be no surprises, no discoveries, no growth. The fragmentation of 3i Atlas, disappointing as it was for casual observers, provided scientists with unexpected data about cometary structure. What seemed like failure from one perspective was success from another. This multiplicity of perspectives, this ability to find value in the unexpected, is perhaps one of humanity's greatest strengths. The comet also raises questions about legacy and continuation. What legacy does 3i Atlas leave behind? Scientifically, it contributed to our understanding of cometary fragmentation. Culturally, it became part of the story of 2020, a year already full of unexpected events. Physically, its fragments continue orbiting the Sun, each carrying forward part of the original comet's substance and story. The dust it shed will orbit for years, perhaps eventually falling to Earth as meteors. In all these ways, 3i Atlas continues despite its apparent destruction. This continuation despite transformation mirrors patterns throughout nature and human experience. Our bodies constantly replace their cells, yet we maintain continuity of identity. Cultures evolve and change while maintaining core elements across generations. Languages transform while preserving ancient roots. Stars die and seed space with elements that become new stars. Everything is constantly changing yet somehow continuous, constantly dying yet somehow persisting. 3i Atlas exemplified this paradox in its brief dramatic appearance in our skies. The philosophical implications extend to how we think about time itself. 3i Atlas connected different moments across centuries, its formation billions of years ago, its possible observations by ancient astronomers, its fragmentation in 2020, the future paths of its fragments. Through this one object, we see how past, present, and future are interconnected. How events separated by vast spans of time can be causally linked. The comet was simultaneously ancient and contemporary, finished and continuing, one object and many. As you lie there, perhaps feeling yourself drifting closer to sleep, you might sense how these philosophical reflections apply to your own existence. You too are ancient and contemporary, made of old materials arranged in a current pattern. You too are fragile yet resilient, temporary yet continuous, one person yet connected to all existence. The story of 3i Atlas isn't just about a distant comet, but about patterns and processes that apply at every scale, from the cosmic to the personal. The comet reminds us that beauty doesn't require permanence. Its tail, magnificent while it lasted, was beautiful precisely because it was temporary, a brief flowering of light against the darkness. The same is true of sunsets, flowers, human lives. Their transience doesn't diminish their beauty, but perhaps enhances it. Knowing that something won't last forever can make us appreciate it more in the moment. 3. Atlas existed as a visible comet for only a few weeks out of billions of years, but those weeks mattered to everyone who observed it. There's also a lesson about scale and perspective. From a human viewpoint, 3i Atlas was a disappointment, failing to become the bright comet many hoped for. From a cosmic viewpoint, it was just another small comet following natural processes. From a scientific viewpoint, it was a valuable source of data. From a philosophical viewpoint, it was a teacher and metaphor. Each scale of observation, each perspective, reveals different truths. The ability to shift between these perspectives, to see things from multiple viewpoints simultaneously, enriches our understanding and experience. The story of 3i Atlas also touches on the theme of prediction and surprise. Despite all our scientific knowledge, we couldn't predict that the comet would fragment when it did. This reminds us that mystery and uncertainty remain even in an age of advanced science. We can calculate orbits with extraordinary precision, but we can't fully predict the behavior of complex systems. This isn't a failure of science, but a feature of reality. The universe maintains its capacity to surprise us, to exceed our expectations and confound our predictions. As we near the end of our philosophical contemplation, we might ask, what would 3i Atlas mean to a hypothetical alien civilization observing from another star system? To them, it would be invisible, too small and faint to detect across interstellar distances. Our entire solar system would appear as a single point of light, if visible at all. The human drama surrounding the comet, the anticipation, the disappointment, the scientific analysis, would be completely unknown to them. This perspective reminds us of our cosmic isolation, but also our uniqueness. We're probably the only observers who witnessed 3i Atlas, the only consciousness that contemplated its meaning. Yet this uniqueness comes with responsibility. If we're the only observers, the only consciousness capable of understanding and appreciating comets like 3i Atlas, then our observations matter cosmically. We're the universe's way of observing itself, of understanding its own processes, of appreciating its own beauty. Every time we observe a comet, calculate an orbit, or contemplate cosmic meaning, we're fulfilling a role that, as far as we know, no other beings are performing. We're the cosmos becoming conscious of itself, even if only partially and temporarily. The fragmentation of 3i Atlas thus becomes not just a physical event, but a moment of cosmic self-awareness. Through our observations and analysis, the universe witnessed its own processes of transformation. Through our disappointment and fascination, it experienced emotional responses to its own activities. Through our philosophical contemplation, it reflected on its own meaning. We're not separate from the cosmos, but its sensory organs, its cognitive capacity, its philosophical faculty. When we studied 3i Atlas, the universe was studying itself. This perspective transforms our relationship with celestial events. We're not just passive observers, but active participants in cosmic self-discovery. Every amateur astronomer who photographed 3i Atlas, every scientist who analyzed its spectrum, every person who simply looked up hoping to see it, all were participating in this process of cosmic self-awareness. The comet story became part of human culture, human memory, human understanding, and through us, part of the universe's understanding of itself. As our journey through the philosophy of fleeting stars nears its end, we return to the central question. What does a visiting comet teach us about our own lives? Perhaps it teaches us that we too are visitors, brief guests in the cosmic home, here for a moment before continuing on transformed. Perhaps it shows us that fragmentation isn't failure but multiplication, that endings are beginnings, that nothing is ever truly lost but only changed. Perhaps it reminds us that beauty doesn't require permanence, significance doesn't require spectacle, and meaning doesn't require cosmic acknowledgement. The story of Three-Eye Atlas is ultimately a mirror in which we see ourselves, temporary arrangements of ancient matter, following paths determined by forces beyond our control, yet somehow capable of choice and awareness, fragile enough to break apart, yet resilient enough to continue in new forms, insignificant on cosmic scales, yet unique in our capacity for observation and understanding. The comet came and went as all things do, but in its passing, it illuminated truths about existence that extend far beyond its own brief appearance. As our journey ends, we return to the quiet mystery, and perhaps this is the most profound gift that Three-Eye Atlas offers us. Not answers, but better questions. Not certainty, but deeper wonder. The question of whether this comet was predicted in ancient texts has led us through centuries of human observation, through the mathematics of orbital motion, through the patient records of civilizations long gone, through philosophical contemplations about time and existence, and now, finally, to a place of peaceful uncertainty. We don't know for certain whether ancient astronomers saw earlier members of the Three-Eye Atlas family. We don't know how many fragments of the original parent body are still out there, slowly approaching their own appointments with the sun. We don't know whether future observers will recognize patterns we've missed, or discover connections we couldn't see. And perhaps this not knowing is exactly where we should be as we drift towards sleep. Certainty, after all, is the end of inquiry, the closing of possibilities, the termination of wonder. But uncertainty, peaceful, accepting uncertainty, is the space where imagination flourishes, where possibilities remain infinite, where the universe maintains its capacity to surprise and delight us. The mystery of Three-Eye Atlas and its possible prediction in ancient texts isn't a problem to be solved, but a doorway to wonder, an invitation to contemplate our connections across time and space, a reminder that we're part of something vastly larger than ourselves, yet intimately connected to everything around us. Think about what we've discovered on this journey, not in terms of definitive answers, but in terms of enriched understanding. We've learned that comets can be families, related across centuries through fragmentation and orbital evolution. We've seen how modern observations can connect to ancient records, how Chinese astronomers watching the sky 2,000 years ago might have been documenting the ancestors of comets we see today. We've understood that the mathematical precision of orbital mechanics coexists with the chaos of fragmentation, that predictability and surprise are both fundamental aspects of cosmic behavior. We've recognized that every comet is both a physical object following natural laws and a cultural phenomenon interpreted through human consciousness. The specific question about Three-Eye Atlas has opened into broader questions about the nature of knowledge itself. How do we know what we know? How reliable are ancient observations filtered through translation, interpretation, and millennia of copying? How can we distinguish between real patterns and coincidence? How do we balance scientific skepticism with openness to possibility? These questions don't have simple answers, but engaging with them deepens our appreciation for both the achievements and limitations of human understanding. Consider how different this mystery is from mysteries in detective stories or puzzles with definitive solutions. The mystery of Three-Eye Atlas can't be solved by finding one crucial piece of evidence or making one brilliant deduction. Instead, it's a mystery that deepens the more we explore it, that opens into other mysteries, that connects to fundamental questions about the nature of time, causation, and knowledge. It's a mystery that enriches rather than resolves, that expands rather than contracts, that leads us not to a single answer but to a constellation of possibilities. This open-ended quality of cosmic mysteries reflects something essential about our relationship with the universe. We're pattern-seeking beings in a cosmos that presents both patterns and randomness. We're meaning-making creatures in a universe that's neither meaningful nor meaningless, but simply is. We're temporary observers of processes that extend far beyond our brief existence. This tension between our human need for understanding and the universe's indifference to that need creates the space where science, philosophy, and wonder intersect. The ancient texts we've examined, Babylonian tablets, Chinese chronicles, Mayan codices, remind us that the quest to understand comets and predict their appearances is as old as civilization itself. Every culture that looked at the night sky and tried to make sense of what they saw was contributing to a conversation that continues today. When we analyze the orbit of 3i Atlas with sophisticated computers, we're using different tools but asking similar questions to those posed by ancient astronomers. The technology has changed dramatically, but the fundamental human impulse to observe, record, and understand remains constant. This continuity across cultures and centuries suggests something profound about human nature. We're not content to simply experience the universe. We need to understand it, or at least try to understand it. This drive to comprehend cosmic phenomena, even when they have no immediate practical relevance to our daily lives, seems to be a defining characteristic of our species. A comet passing through the outer solar system doesn't affect our ability to find food or shelter, yet we spend enormous resources tracking it, studying it, trying to understand its nature and predict its behavior. Why do we do this? Perhaps because understanding our cosmic environment, even partially, gives us a sense of place and purpose. Perhaps because the quest for knowledge is intrinsically rewarding, regardless of practical applications. Perhaps because we intuitively understand that we're part of the cosmos, and understanding it means understanding ourselves. Whatever the reason, the fact that humans have been watching comets for millennia, recording their appearances, trying to predict their returns, suggests this isn't a cultural quirk but something fundamental to who we are. The fragmentation of 3i Atlas adds a poignant note to this ancient quest. Just as we were beginning to understand this comet, to calculate its orbit and predict its behavior, it fell apart, transforming from a single object we could study into a dispersed cloud we could barely observe. It's as if the universe was reminding us that our understanding is always partial, always provisional, always subject to revision when nature reveals new aspects of itself. The comet's fragmentation was both an ending and a beginning, the end of 3i Atlas as a single object, but the beginning of new questions about cometary structure and fragmentation processes. This transformation from one mystery to many mirrors the evolution of scientific understanding more broadly. Every question we answer generates new questions. Every discovery opens new areas of ignorance. Every pattern we identify reveals exceptions that need explaining. This isn't a flaw in science, but its greatest strength. The ability to continuously refine and expand our understanding, to remain open to new evidence and new interpretations, to embrace uncertainty as a doorway to discovery. The possible connection between 3i Atlas and ancient observations illustrates how science builds bridges across time. When we calculate that the comet's parent body might have appeared in 1244 CE, we're using mathematical tools to reach back across centuries to potentially connect modern observations with medieval records. This temporal bridge building is unique to astronomy. In no other science can we so directly connect contemporary observations with historical records spanning millennia. The sky is our common heritage, observed by every human culture, recorded in various ways but describing the same phenomena. Yet these bridges across time are fragile, built on assumptions and approximations, vulnerable to errors in calculation or interpretation. We can't be certain that the bright comet recorded by Chinese astronomers in 1264 was related to 3i Atlas. We can't prove that Babylonian references to wild sheep stars describe comets rather than other phenomena. We can't know for sure whether ancient observers recognized patterns that we're only now rediscovering. These uncertainties aren't failures but reminders of the limits of knowledge, the boundaries of what we can know about the past through present observations. As you continue to rest, perhaps feeling the gentle pull of sleep, consider how the story of Three-Eye Atlas connects you to observers throughout history. When you learned about this comet, when you wondered about its nature and origin, you joined a tradition stretching back to the dawn of civilization. You became part of the great human project of trying to understand the cosmos. It doesn't matter whether you're a professional astronomer or someone who simply read about the comet in the news. By paying attention, by wondering, by caring about a small icy object millions of miles away, you participated in humanity's ongoing dialogue with the universe. This dialogue doesn't require sophisticated equipment or advanced degrees. It only requires curiosity and attention. The ancient astronomers who might have observed earlier fragments of the Three-Eye Atlas family had neither telescopes nor computers, but they had what we have: the ability to observe, to wonder, to record what they saw and try to make sense of it. Their observations, carved in clay or written on papyrus, preserved in ways they never could have imagined, now help us understand the history of comets across centuries. Our observations, recorded in digital databases, might similarly help future astronomers understand patterns we can't yet perceive. The question of prediction adds another layer to our contemplation. Did ancient astronomers actually predict the return of comets? Or did they simply record appearances without understanding the cyclic nature of orbital motion? The answer probably varies by culture and period. Some ancient astronomers certainly recognized that certain celestial phenomena are repeated: eclipses, planetary conjunctions, the appearances of some comets. But the long periods of comets like those in the Three Atlas family, spanning many human generations, would have made pattern recognition extremely difficult without written records maintained over centuries. This highlights the importance of institutional memory in astronomy. No individual can observe a comet with a 600-year period twice, but institutions, observatories, libraries, cultures can maintain records across multiple returns. The Chinese Astronomical Bureau, operating continuously for over 2 millennia, could potentially have observed the same comet family multiple times. European monasteries, maintaining chronicles across centuries, might have recorded multiple appearances without recognizing the connection. Only now, with our ability to calculate orbits precisely and access historical records from multiple cultures, can we begin to see patterns that were invisible to individual observers. The story of Three-Eye Atlas thus becomes a testament to collective human endeavor across time. Every observation, whether by an ancient Chinese court astronomer, a medieval European monk, a 19th century scientist, or a modern amateur with a digital camera, contributes to our growing understanding. We're all part of the same project, separated by time and culture, but united in our attention to the sky. The comet doesn't care who observes it or when, but through our collective observations we build an understanding that transcends individual limitations. As we approach the true end of our journey, it's worth reflecting on what we've learned, not facts and figures, though those have their place, but deeper truths about the nature of cosmic observation and human understanding. We've learned that comets are more than dirty snowballs. They're messengers from the early solar system, carriers of water and organic molecules, fragments of larger bodies with complex histories. We've learned that ancient astronomers were more sophisticated than often assumed, maintaining careful records that still have scientific value today. We've learned that the universe operates on multiple timescales simultaneously, from the seconds of human perception to the billions of years of cosmic evolution. Most importantly, perhaps, we've learned that questions can be more valuable than answers. The question of whether Three-Eye Atlas was predicted in ancient texts has led us through physics and philosophy, through history and speculation, through certainty and uncertainty. It's shown us connections we might not have otherwise seen, patterns we might not have otherwise noticed, mysteries we might not have otherwise appreciated. The question itself has been a comet, drawing us along a trajectory through various fields of knowledge, illuminating different aspects of human understanding along the way. And now, as you drift towards sleep, you carry with you not the burden of unanswered questions, but the lightness of cosmic perspective. You know that you're made of star stuff, that comets might have brought water to Earth, that ancient observers watch the same sky you see, that the universe is vast and mysterious and beautiful. You know that Three-Eye Atlas came and went as all things do, but that its story continues in the fragments still orbiting, in the scientific papers still being written, in the memories of those who observed it, in the questions it raised that we're still trying to answer. The night continues around you, peaceful and vast. Somewhere above, beyond your ceiling, beyond Earth's atmosphere, the fragments of Three-Eye Atlas continue their journeys. They're too faint to see now, but they're there, following their new orbits, carrying forward the ancient ice and dust that once formed a single comet. Other comets are approaching, some known, some yet to be discovered. One might be another fragment of the Three-Eye Atlas family, returning after centuries in the darkness, or it might be something entirely new, a first-time visitor from the Oort cloud carrying secrets we haven't yet imagined. The universe continues its patient unfolding, indifferent to our observation but somehow enriched by it. Every time we look up, every time we wonder, every time we try to understand, we add our small contribution to the cosmic story. We're the universe becoming aware of itself, even if only partially, temporarily, imperfectly. Through our eyes, the cosmos sees its own beauty. Through our minds, it contemplates its own mystery. Through our questions, it explores its own nature. The story of Three-Eye Atlas, its discovery, its approach, its fragmentation, its possible connection to ancient observations, becomes part of this larger narrative of cosmic self-discovery. It's a chapter in the book the universe is writing about itself, using us as both authors and readers. The book is far from complete. Indeed, it may never be complete. But each observation, each calculation, each moment of wonder adds another page, another paragraph, another sentence to this ever-growing story. Sleep is approaching now, that daily journey into mystery that mirrors the larger mysteries we've been exploring. As you drift off, you might dream of comets streaming across ancient skies, of patient astronomers recording their observations by candlelight, of ice and dust swirling in the darkness between stars. Or you might dream of completely different things, your unconscious mind processing the day's experiences in its own mysterious way. Either way, you're participating in cycles within cycles, the cycle of sleep and waking, the cycle of Earth's rotation, the cycle of comets returning from the darkness. Tomorrow, the universe will continue its patient unfolding. The fragments of Three-Eye Atlas will be slightly farther along their orbits. Ancient light from distant stars will reach Earth for the first time, somewhere perhaps. An astronomer will discover a new comet, adding another data point to our growing understanding. The questions we've explored tonight will remain largely unanswered, but that's as it should be. In a universe where everything was known, where all mysteries were solved, where prediction was perfect and surprise impossible, there would be no room for wonder. So rest now in the peaceful uncertainty, the gentle not knowing that leaves space for possibility. The universe is vast and you are small, but you're the small that can contemplate the vast, the brief, that can perceive the eternal, the finite that can imagine the infinite. You're stardust that has temporarily arranged itself into a pattern capable of recognizing its own nature, of wondering about its origin and destination, of finding beauty in the brief appearance of a comet that most people never even knew existed. The question that brought us here, was Three-Eye Atlas predicted in ancient texts? Remains open, a door rather than a wall, an invitation rather than a conclusion. Maybe ancient astronomers saw earlier fragments of this comet family and recorded them in ways we haven't yet recognized. Maybe the patterns we think we see are just coincidences, our pattern-seeking minds creating connections where none exist. Maybe the truth is somewhere in between, Or maybe it's something we haven't even considered. The universe keeps its secrets while slowly revealing them, maintaining the mystery that makes existence interesting. And so our journey ends where it began, with wonder. Wonder at the cosmos that created us. Wonder at our ability to observe and understand it even partially. Wonder at the connections between past and present, between earth and sky, between the cosmic and the personal. 3i Atlas has completed its performance and exited the stage, but the theatre remains, the show continues, and we remain in the audience, watching, wondering, occasionally understanding, always amazed. Close your eyes now if they aren't already closed. Feel yourself sinking into comfort, into rest, into the peace that comes from accepting our place in the cosmic order. You're part of something infinitely larger than yourself, yet you're unique in your ability to perceive and appreciate it. You're temporary yet connected to the eternal, small yet significant. A brief note in a cosmic symphony that has been playing since time began and will continue until time ends. The comet came and went, as comets do. Ancient astronomers might have predicted it, or might not have. We may never know for certain. But in searching for the answer, in following the trail of evidence and speculation across centuries, we've discovered something perhaps more valuable than certainty. We've discovered the depth of our connection to the cosmos and to each other across time. We've discovered that questions can be as valuable as answers, that mystery can be as satisfying as solution, that wonder is not just the beginning of wisdom, but perhaps its culmination. Sleep now, carried on the gentle waves of cosmic time, dreaming perhaps of comets and stars, of ancient observers and future discoveries, of the vast universe that created you and that you, in your small way, help to understand. The night is peaceful, the cosmos continues its patient spinning, and somewhere in the darkness ancient ice carries on its eternal journey, waiting for the next moment when it will fall toward the sun and briefly, beautifully, become a comet once again. Rest well, fellow traveller, fellow observer, fellow arrangement of cosmic matter capable of wonder. The universe continues, and you are part of it, now and always, in sleeping and in waking, in knowing and in mystery, in the eternal dance of matter and meaning that we call existence.